can start. It's okay. Hello, everyone. Welcome to our last day of Pass the Salt. We have a first presentation today about the security of Kubernetes. Our first speaker today is Magno Logan. So, Magno, you can start to share your screen.
Okay, thank you.
And you have 35 minutes.
Okay, thank you. Sounds good. Okay. Can you see my screen?
Yeah, it's okay.
Yes, perfect. Thank you.
Awesome. Okay, thank you. So yeah, welcome everyone. Good morning, good afternoon, and good evening from wherever you are. Right. This talk is about attacking Kubernetes, technical deep dive into the attack for containers. My name is Magno Logan, and I work for Trend Micro here in Canada. So yeah, just a little bit about myself. Let me introduce you. I work as an information security specialist and a senior threat researcher at Trend Micro. Also, I'm a member of the cloud and container security research team, and also a member of the CNCF security tag team, which is a specific group of volunteers that helps the CNCF build. The CNCF means Cloud Native Computing Foundation, which is a foundation, a sub-foundation of the Linux Foundation. And we help them advising and creating documentation and guidance around security of cloud native tools, including Kubernetes. I don't consider myself a Kubernetes security expert yet. I'm still learning, and Kubernetes is a very complex system, and there is a lot of stuff, a lot of things going on behind the curtain. So yeah, I'm just here to share my knowledge and what I've learned over the past year studying and researching Kubernetes, and also the work that we did with MIBR to release this attack for containers matrix. I also have a personal blog there, katanasec.com, where I try to release a blog post at least once a month. And there's also all my contact information, like my social network, LinkedIn, GitHub, and Twitter, and also all my previous talks. So slides or videos of previous talks that were recorded are all there, and you can find it there as well. So yeah. That's it about me. So yeah, we have a lot to cover. This is the agenda. I won't go through everything now, but we'll try to cover at least most of it today. And if not, then I'm open to discussions and questions at the end. But yeah, feel free to let me know if you have any issues, or if you want to know a little bit more about any specific topic that we discussed here today. Before we start, I just like to let you know that I created this GitHub project, which is called the Awesome Kubernetes Security List. It's basically a list of resources for you to learn Kubernetes and Kubernetes security. It has everything from the basics of understanding how Kubernetes works sometimes in very much detail and behind the curtains. And it also has a lot of presentations and articles and videos from other speakers and other professionals around Kubernetes security. So it's been almost, I think, more than 6 months, 8 months, I think, that I created this list. It was just for myself. Basically, I had a long text file with all those notes, and I decided to share, and people started contributing, and it's become a big project now. So I think it might be helpful for you if you're taking that Kubernetes and Kubernetes security journey. So yeah, that's the link right there, and feel free to share and contribute that with other people. Okay, so attacking Kubernetes, right? So yeah, I don't know if you noticed the kind of the play in the words there in the title, but we're going to talk about the MIBR attack framework, right? If you don't know what the MIBR attack framework is, right? So I'm just going to give you a little overview here. It's basically a framework created by MIBR that contains adversarial tactics, techniques, and common knowledge, right? Okay, but what does that mean? It's basically a globally accessible knowledge base of opposing tactics and techniques based on real world scenarios. Okay, I still don't understand what you're saying, right? Okay, it's basically whatever the attackers are doing in the wild or researchers are finding through their research and honeypots. So on real world scenarios, they categorize it and they have a proper structure of tactics and techniques and sub-techniques as well. And they also list the attackers, right? So they have the threat actors, what they're doing, which kind of industry they're targeting. So it's very common now in the security industry, and I hope you are aware of it. If not, I really recommend you take a look. So it's used as a basis for the development of specific threat models and methodologies in many different sectors, right? So how does that help me, right? So specific techniques and tactics are hard to change. I don't know if you've seen the period of pain of David Bianco, right? But hashes and IP addresses can be easily changed by the attackers, right? But techniques and tools and procedures are harder for them to change because those are their habits and those are the knowledge that they have. So once you have that and you categorize and you have a list of that, you understand who's targeting you and what is their MO, right? So, and then you can specifically target your defenses and your logging and all your procedures for incident response towards those techniques and towards those most famous tools and attacks, right? So that's very helpful, not just for defenders or blue teamers, right, into finding and protecting their environments, but also for red teamers and either like purple teamers as well. And I won't get into the color discussion here, but like if they want to simulate a specific threat actor or threat group, right, they can use the same techniques that they're using or that they've used in the past against other companies, right, or other organizations. So yeah, so basically we worked with MIBR to create, the MIBR has different matrices, and we work with them to create the attack matrix for containers, right? There's many different ones now. There is the one on enterprise, there's one for Linux, one for Windows, and one for cloud, right? But we didn't have one until this year. We didn't have one for containers and Kubernetes as well, right? So the attackers are already leveraging those environments and those technologies to compromise Docker and Kubernetes, mostly to mine Bitcoins, as we're going to see that in the next few slides. But they're leveraging that, right? If you're not protecting those environments, then you can be compromised, right? So I'm just going to give a quick timeline here of how this project, how the whole project all started from my perspective. Not MIBR's perspective, but that's basically what we've learned and how we worked with them. So yeah, the timeline there was before even the MIBR attack for containers project started, there was a matrix that was released by Microsoft in April last year, which they call the Kubernetes threat matrix, right? So it wasn't an official MIBR matrix, but it had the similar approach with the tactics and techniques, right? So that's what, and it was limited to what they were seeing, the attacks that they were seeing on Azure, right? The Kubernetes managed service for Azure, the AKS actually, right? So it was very limited. It was geared towards Microsoft and Azure environments, right? So it was okay. It was great. It was a good start, but it wasn't enough. It didn't cover a lot of all the different other environments of Kubernetes, like EKS and GKE and on-premises environments and bare metal and all that stuff, right? So in December last year, MIBR released a blog post asking for help for the community to build that matrix, right? So there was a blog post by the MIBR tech lead for cloud and containers, Jen Burns, asking for any kind of information that companies and organizations in the security community were able to share and to help them build that matrix and what we've seen in the wild. And since we're working with cloud and container security research already, we have many different honeypots on Docker and Kubernetes now about like with a lot of information on what the attackers are doing, right? So we analyze this kind of logs and triggers kind of on a daily basis. So we know, and we've published many different articles around vulnerabilities around those environments, right? So on the next day, we talked among our team, and on the next day, basically reach out to them and provided the reports and the information that we have released and some other stuff as well, some other data for them. After that, there was basically a first draft that was released in January that they provided to us, and it was released to the public in February for review and comments and feedback. And during that time, and before the attack for containers was released, Microsoft had updated their Kubernetes threat matrix that they had released last year, right? So that was kind of appropriate. They updated that, and I'm going to show that in the next slide. And basically what we have now, it's in April 29th this year, the attack for containers. And I talk about, when I say attack for containers, I'm meaning attack for containers and Kubernetes, because it also has some Kubernetes specifics or container orchestration specific techniques. So it was released there, and it was right before KubeCon Europe this year. And yeah, that's available right now. If you haven't heard about it, I hope you have, but if not, then I highly recommend you take a look. So what I'm gonna show here is basically, this is the Kubernetes threat matrix from Microsoft. This is the updated version. You can see here in red, there are some deprecated techniques, and in green, new ones that are similar to the MIBR framework. This is not the official one, the official MIBR matrix, but just to be aware if you want to learn more about it and what Microsoft and Azure are seeing in their environments. So that's that. But here is the official one. Here's the one that we're going to discuss today, and what we call the official MIBR attack for containers and Kubernetes, right? It's not as big as the other ones. If you've seen the previous MIBR matrices, they are very large, and sometimes they can't even fit on a single slide, right? And this one, for now at least, we can fit on a single slide. So I think that's pretty good. It's not a lot of stuff, so attackers are not too sophisticated on those techniques yet, and there's not a lot of ramifications and sub-techniques, but it's a good start. It's a way for you, if you're deploying or if you have Kubernetes and container workloads in production, right? You need to be aware of those techniques, right? Some of them are similar to what already existed in Linux and other enterprise matrices, but now with a focus on containers and references for containers, and some of them are brand new techniques. So the work that we did, and not just Trend Micro, but other organizations as well, that we did with MITRE, we shared information from our research and from what we've seen in our honeypots, and they worked out the techniques and categorized them in specific tactics, right? So basically, we contributed overall with 25% of this whole matrix. So 7 techniques, 5 ones which were already existed, but we contributed with information about container-specific scenarios and attacks and techniques, and also 2 brand new techniques as well. So we're going to talk about that in the next slides. And before that, before even this was released, when I started my Kubernetes research, I started like doing some kind of threat modeling, if I may say that, on Kubernetes environments, right? So basically what we do is we understand, okay, what are the vulnerabilities, what are the issues on those environments, right? And basically, I know it might be a bit hard to see here, but and I can share this diagram later with everyone. But here, what I did was trying to create a threat modeling approach where someone would compromise web application that was running inside a pod, which is like the smallest unit of Kubernetes, right? And that pod, right, had permissive privileges, right? Or too many privileges that were able to, for the attacker, would allow the attacker to either compromise the environment or deploy other pods and other containers, right? And so basically this is the diagram. And once we model this, then we go to the POC, right? Okay, let's test it. Let's see if that works and what are the specific requirements or prerequisites for this scenario to work, right? Is that like a default configuration, or does it have to be a misconfigured cluster on purpose, right? So we did that, and the end goal there at the end, as you can see, each swim lane is a tactic from the MIBR framework. So I already did that based on the MIBR attack framework, because we use that a lot on our daily basis. But at the end there, the impact, as you can see, can be data dump or destruction. It can be denial of service, but most of the times, and I would say like 90 or even more than 90% of the times, the impact is resource hijacking, right? And what that means by resource hijacking, crypto mining, right? So they deploy crypto miners, usually Monero crypto miners, to mine cryptocurrencies, right? So yeah, so that's usually the end goal here, and so that's what we worked, and that's when we tried modeling, we POC that everything worked, and now we're going to correlate some of those techniques to the MIBR and show how attackers are leveraging that on attacking environments in the cloud and on premises as well. So the POC that I did here was basically a vulnerable web application, right? I didn't create a fake web application. I used a real one, which is, you can see here, it's a Drupal CMS, right? I just made some edits there on the interface, but it's a Drupal CMS, content managed system, right? And the version that I'm using here, it's the version A.5.0, which is specifically, it's from 2018 and specifically vulnerable to an RCE, right? Remote command execution vulnerability called Drupal-Geddon. And so once I execute that RCE into that application running on my cluster, I get a shell into the pod of the Drupal container, right? So basically that's what I'm looking for here. First, I need to get a shell into the cluster or somewhere into the pod to be able to start doing my attack. So one of those techniques that it's part of the attack for containers, and it's already it was already there, but not with the focus for containers in Kubernetes, is exploit publicly facing application, right? So we know that applications are the main entry point of attacks nowadays. Everything is kind of on the web and online, and a lot of things are exposed even if you don't know, right? So in this scenario, we are exploiting this specific CVE from 2018 called Drupal-Geddon to get a shell, but it could be anything. It could be any other application that has RCE or a command injection vulnerability, right? And it could be any other web app. So be careful. Even if it's a customized web application, if the attackers can find a vulnerability or RCE or command injection that they can inject commands and send commands to your container, that's very risky, right? So it's not just having protecting the infrastructure and your Kubernetes cluster that's enough, right? Your code and your web applications need to be protected as well. One other issue that we used to have before, but luckily was disabled by default, was the Kubernetes dashboard, which used to be installed by default in previous versions, and it was exposed and didn't have proper authentication. That's even why the Microsoft Threat Matrix deprecated that, because we don't have that by default. So someone needs to liberally expose that and install that before exposing, right? But we still have the Kube API server. And if you haven't heard about the Kube API server, it's just a regular API server like any other, like a REST API. And it shouldn't be exposed to the internet, right? It shouldn't be exposed publicly unless you have a specific reason to do that and you protect it properly. But the problem is when using managed services like EKS from AWS, your Kubernetes server, your Kubernetes API server endpoint is public by default. So I don't know if you know about that, but if you have some Kubernetes clusters running on AWS, I really recommend you checking that out and see if you need to really expose that and leave it public or turn that to private, right? So the API endpoint, just like the Docker API, it's basically where I send all the commands to my Kubernetes cluster, right? So I don't have time to go into the whole Kubernetes architecture here, and I hope you have at least a little bit of knowledge, but everything goes through the API server on the control plane and also on communications on the worker nodes, right? So it receives all the communication, and that's how I tell my cluster to create new pods and create new containers, right? So if that exposed and that's not properly secured through RBAC, role-based access control, then we're gonna have a lot of issues. So what we do, one of the basic things that we do in our honeypots is exposing a Kubernetes cluster with the API server open and open to the internet, and anyone can do anything, right? So it's kind of okay, full permissions and cluster admin. Of course, that's not a good thing to do, but we want to see how the attackers are doing and how they go from there on compromising a Kubernetes cluster. Another technique that we have here from the container attack for containers, right, is the container administration command, right? So basically reaching the API endpoint, as I said before, and also not just the Kubernetes server API, but the Docker daemon API as well. So some honeypots, we just expose the Docker daemon API, and they do that. And if they have the proper permissions, they can deploy containers and do anything, and deploy even privileged containers to break out of the container or the pod itself and access your nodes, right? Your Docker host or your Kubernetes nodes, and that goes. We've seen attacks where from the API server, they deployed how can I say? They deployed privileged containers into the cluster, a new container or a new pod, and then breaking out of the cluster, right? And now they have access to the environment, to the nodes. They got access to the API keys of the specific instance. It was running on a cloud instance there. And now they have those keys, and they could use those keys to deploy new instances, which they did, and deploy those new instances to mine cryptocurrencies, right? To mine Monero cryptocurrencies. And some of these attacks that we did, some of those simulations, it took less than 24 hours for the attackers to perform all this. We didn't publish anything, right? We created the cluster and it was on a public API endpoint, but we didn't publish the URL or the IP anywhere, like not even on Pastebin, anywhere. We just created. But since they're scanning the network and they're scanning specific endpoints for those managed services, because they have, as you can see here on the second URL here, they have a specific pattern of endpoints and URLs. So they're scanning that and they're looking to find active clusters that are exposed and vulnerable, right? So be very aware of that and be very careful when exposing your Kubernetes API server. So yeah, what's the end goal here, right? Getting shell inside of one of the pods from the cluster, right? It could be the exposed dashboard if it's an outdated cluster, but it usually is a vulnerability on the web application itself, right? But the end goal is getting a shell or being able to execute command inside that pod, inside that container. But what happens next, right? Here it's also another script that we found from one famous threat actor called Team TNT. and we've been researching them and publishing some papers around them very closely. And this part of the script here, I don't know if you can read it properly, but it's running after they compromise the network of your organization, right? They don't care if your Kubernetes API server is exposed or if they can access it from the internet, right? They don't care about that. What they do is they compromise your environment, and once they're in, they do a mass scan, right? They download the mass scan from, which is a famous scanning tool that's very fast, and they download that from GitHub, and they do a mass scan on specific port 10.250, right? 10.250, which is the kubelet port, right? And they look for anything that's running on this port, any kind of server that has this port open and is responding, but they're inside a network already. Even if you don't have that kubelet port exposed to the internet, now they can check if you don't have proper network segregation and mitigation there. So once they do that in this script, this function that they called kubePwn, right? PWN, they check for the running pods. So there is a specific endpoint on the API, which is not documented by Kubernetes, the official documentation on the kubelet API. So we had to read through the Kubernetes code, which is written in Go, to understand what they're doing here, like what's their end goal. I know it seems kind of straightforward, right, when you see it, but we wanted to confirm from the code itself, right? So running pods here, when they check the kubelet, the IP of the node and the kubelet port, running pods of course, it's gonna tell them which pods are running in that node, right? So they get some information using JQ, the namespace, the name of the pod, and specific containers if they're running multiple containers, right? I don't know if you know about that, but the pods on Kubernetes, they can run multiple containers, right? You can have one container running in one pod, but you can have more than one container sometimes, which is called the sidecar container. So once they have that information, now they're they're doing some updates and installing like bash and curl and wget to then install their crypto miners. So they have a specific URL. They have a command and control server, which we're able to find, where they store the binaries of their crypto mining tools, right? Their Monero tools. So they download that from that server and install on those pods and start them at the end of the script here. They start and they leave it running on the temp folder, right? So this is just part of the script that what they do. We've published a blog post about it recently. I think it was last month. It has more details, but it's very specific here on what they're targeting, and it doesn't need to be exposed to the internet, right? So it might be even internal on the network. That's why it's important to have proper segregation on who can access your Kubernetes cluster from inside your network as well. Besides that, there is also some container and resource discovery techniques, right? There are some basic techniques that you can use to find out if you're in a Kubernetes or a Docker containerized environment, right? So basically, one of the main things that you can check is for environment variables, right? So every pod should have environment variables related to your Kubernetes cluster. So if you do this command there, grabbing for kube environment variables, you're gonna find something and it might tell you if you're in a Kubernetes pod or not. Another thing is the service account token, right? Every pod has, by default, has a service account. That's basically some files is stored on that specific directory there, and it's always on the same directory, right? So you know exactly where to find them, and you can use that service account and token to talk to the API server, pretending to be the pod, right? So communicating with that, and so you can send that token and impersonate that pod itself and ask for more information if you have from that service account. But also there is another tool, open source tool on GitHub that's called MI Contained, right? And my container is a container introspection tool that you can download from GitHub, run on a specific environment, and it's going to find out what container runtime is being used, as well as features available like capabilities and if app armor is enabled, if ACID Linux is enabled, and all that stuff. So those are kind of the main 3 things that some attackers might do to see if your environment is it's a Kubernetes cluster or another kind of cluster or a Docker environment, right? So be aware of that as well when you see those commands running on your environment, and maybe it could be suspicious. Another thing that they do for container resource discovery here is they use mass scanner, right? I showed that in the previous slide there with the kubebound function, but here we can also see that they're downloading directly from GitHub, and I think that might be one of the reasons why GitHub has changed their policy around security tools and exploits on being hosted on GitHub. But we've seen that a lot. We've seen that the attackers don't even need, sometimes they don't even need a command and control server. Everything gets downloaded from GitHub or download from somewhere else, and they can, it's better for them to leave no traces or leave a server exposed with all their tools and sensitive information, right? So yeah, they can leverage that. And same thing with mass scanner, the same thing that they do with zgrab, which is another banner grabbing tool. And funny enough, this banner grabbing tool here is outdated. It's the version the version that they're using. It's the zgrab 1. It's deprecated. It's not even recommended anymore. So so they're not even downloading the latest versions, which is kind of funny. I don't know, but yeah. Let's see. Another technique here, deploying containers, right? As I said, like the way you can compromise an environment, and the way that sometimes we set up our honeypots is allowing the attackers to deploy containers easily without any kind of authentication or privilege, right? They have the privilege already. They don't need to escalate privileges. That's what I mean. So we can see here from analysis on our Wireshark, right, from our previous blog post here as well, that they can easily create that. They can easily create containers, and they're doing that if they have the proper permissions, right? So, you know, it seems kind of obvious, right, deploying a container. But if you have the proper controls and you have like admission controllers and runtime security, you can prevent those containers from being deployed, right? If those containers are not, they don't comply with the policy that you have. Like, for example, those containers are not being downloaded from your private registry. They haven't been scanned by security vulnerabilities, and they don't have any kind of critical vulnerabilities, right? You don't allow them to be deployed. So it's a simple thing that you can use an admission controller and some tools like OPA and Kyverno to help you with that. And the problem with deploying containers as well is the container scaping, which I'm going to show on this next slide, right? So deploying containers, then I can do these 2 other techniques here, which are scaping to hosts and exploitation for privilege escalation, right? So there's a common technique here that was disclosed by Duffy Cooley, which used to work for VMware and Apple, and now he works for Isovalent, which is the developer of Cilium. Cilium is a famous container CNI solution. So he disclosed this in 2019, May 2019, so over 2 years ago, and still works today, right? It still works. So on the left side, I have his tweet that I took a screenshot that's still available on the internet. I just took a screenshot to show you here. And on the right side, I have basically the JSON part of it, broke it down into lines so that we can easily understand. Right?
Magno, you
yes?
have 1 minute left.
Okay, sounds good. Yeah, I'm about to finish. I'm just gonna wrap up this part, and we leave the defending part for another day. So yeah, first we see that the kubectl run gets a pod with a container, right? But the overrides argument here makes it special, right? It overloads the spec with a partial set of values parsed from this JSON here, right? First, we see the host PID set to true, which breaks the most fundamental isolation of containers, right? Letting us see all the processes as if we're on the host, right? Next, we see end-center commands switch to a different namespace, right? And the results here is, okay, there's a privileged container mapped to my worker node, right, in my node here. So basically, this was shown by Duffy Cooley, and it was presented on a workshop on KubeCon NA 2019 as well. And the website that I referenced here is securekubernetes.com. So I believe I'm out of time, and I hope you enjoyed this presentation. I had a little bit of part talking about defending Kubernetes, but I won't be able to cover that, and we can talk more about it on the Q&A session on the chat. Thank you.
Thank you.
Thank you.
So much. Is anybody ask question?
Okay. I had one question. Well, it's kind of non-technical question, but I was surprised at the beginning of your talk. It seems like that all initiatives towards Kubernetes security came from like external actors like Microsoft and MIBR. Are the people from the Cloud Native Computing Foundation, are they implied in this MIBR attack scenarios and this project?
Okay, yeah. So the CNCF, the security tag team, I think wasn't involved on the MIBR for containers framework, but specific members of the CNCF were involved through their companies, through their organizations, right? So because the security tag team doesn't have real world scenario data, they don't have honeypots, or they don't analyze that stuff, right? So that's not their goal. Their goal is more on the defense part and building kind of guidance and documentation and helping other projects with the audit of the security of those projects, right? So they don't do much of that work, but I know that specific members of besides me, other members from other organizations such as Palo Alto and Cisco and Microsoft as well, they're also part of the CNCF that they helped with information and data on this project. Yeah.
Okay, so yeah, they are currently really involved in with many people in the MIBR project too. Okay.
Mm-hmm. Yeah.
And well, another thing that I was wondering is the script examples that you showed, were they from your own work, or is that something that you have seen on real containers that you manage or watch for clients?
Those scripts are from the threat actors, right? So these are either from our honeypots that they attacked, or either from their command and control server, right? That we were able to find and collect all that information. So we analyze, and the code that's we didn't change anything there. Those scripts are exactly as we found them, and then we just analyzed to understand what they're doing, but we didn't change anything there. Yeah.
Okay, I think actually, yeah, this shows really what is the state of the risk today. Yeah,
exactly.
That's
right.
really interesting. And maybe one last question. So if I understand correctly, this project, this MIBR project, was based on Kubernetes at first, but does it concern also, or does it address the risk for other kinds of container management systems? Do you think?
Sorry, say that again.
Just this matrix that you showed, it's not only for Kubernetes, I guess it's also for other kinds of container management systems.
Yeah. So we're like us, not just us, but MITRE as well. They were still not sure if they were going to do 2 separate matrices, one for just Docker or containers in general, and one for Kubernetes and other container orchestrations, right? Like Mesos and Nomad and kind of OpenShift, which is basically Kubernetes, right? Other stuff. But they decided that they didn't have enough data, enough, like they need real world scenarios, right? They don't add those techniques if they haven't seen in the wild, right? It can't be a POC, it can't be something that I did from my own research, right? It has to be someone really using those techniques to attack someone, right? To attack an environment, the real environment, right? So I think we didn't have enough data on the other container orchestration tools to evaluate if it was necessary. So I'm pretty sure, and I'm not saying that from my perspective, MITRE might have a different one. I'm pretty sure that this matrix, this container, the attack for container matrix, is mostly focused on Docker environments, simply Docker, and Kubernetes environments, which are mostly using Docker, right? So I think that applies to that. It might be helpful. Some of the techniques might apply to other container orchestrations, but we haven't tested and we haven't seen attacks in the wild yet.
Yeah, okay. So yeah, it's really based on a real example that have been seen on Kubernetes and Docker platforms.
Yeah, exactly.
So I guess we're out of time for questions, so I will stop there.
Okay, sounds good.
Thank you.
Yeah, no problem. Thank you.
Bye.
Thank you. Have a nice day. Bye.
Okay, so our next presentation is about obfuscation technique for shellcode, and it will be presented by Harpreet Singh and Yashdeep Saini. You can start screen sharing. Okay.
Hey guys, can you see me?
Yeah, I can see you on you. That's perfect. Thank you.
Yes.
So you have 35 minutes for your presentation, included the question. Okay.
Okay. Thanks.
Perfect.
So let me just share my
You
screen.
can start.
Just a sec. Could you guys confirm if you're able to see the screen?
Yeah, we can. That's perfect. Thank you.
Awesome. So hey everyone, and it's I think it's good morning over there, or maybe afternoon. It's actually evening here itself. So we are from India. Me and my co-presenter Yashdeep. So he's also there. Yashdeep, can you wave? Awesome.
Hello everyone.
Yeah. So for this talk, we are basically focusing on the shellcode encoding techniques that we have till now, and what kind of latest information that we have received, and more like these techniques that we use on an everyday basis can definitely help you out in bypassing some antivirus and EDR solutions as well. Of course, we are not covering EDR bypasses here, so there's no API unhooking or kernel callback bypass in here, so please don't expect that. But hopefully you enjoy the talk. So let's just begin. So I'm Harpreet, and I have like approximately 8 years of experience in pen test, network exploitations, and I have done a few red team engagements. And yes, I'm kind of bloating about this. I'm also an author, just a normal author, and definitely a animal lover here. Yash, could you introduce yourself?
Yeah, thanks, Harry. Hi, guys, I come from the similar background, but I mainly get involved with system internals and low-level exploitation. So I am not as experienced as Haspreet, but I have worked with them, and I think we can continue on the.
Okay. So let's just have a disclaimer first. This is the information that we have shown. Okay, it's nowhere it's related to our organization, and we specifically don't want to say out loud like which organization we belong to. But for the sake of this presentation, we are just independent researchers, and all the information that we have also presented. So it's I hope we are not, have any issues with the licensing. So I hope we are not violating any kind of licensing issues over here. And a good thing is we have already added the references and sources from where we have got the information. And of course, we have did a comparative analysis, all that in shellcode encoding and stuff. Also, this talk is targeted towards beginner and intermediate level experience. So we are talking about like someone who's really interested into shell codes and maybe have done a shell code course, maybe from Pentester Academy. That's a good place to do the course. So some known information, some knowledge about shell code, that would be good. But we are trying to push this towards a little bit more advanced level. And of course, because we don't have enough time for the talk itself, so it's kind of a compressed version, this talk. So for the agenda, for this talk's agenda, we are talking about, we have to understand about encoders and decoders and what exactly we are doing in comparative analysis for the instruction sets for architectures like 32-bit, 64-bit ARM architectures as well. But these architectures, we have some commonly used encoding, commonly used instructions for these encoding and decoding purposes. So we'll be covering all that in this talk. And also we have there's a process of building a stealthy encoders and decoders. So we'll be going through what all encoders we have. Of course, we are not going through every encoder there in available online, but we are just selecting a very few ones which we found very interesting. So we'll be discussing about that and a little bit changes in that can help us out. And also this talk will also cover the idea itself of developing encoders, but at the same time we'll be covering obfuscation techniques, like the basic encoding stuff, what is polymorphism, metamorphism, polymorphism, basically morphism, and ultimately about mutated shellcodes and polyglots. So at the end of the talk, we'll be focusing on analyzing few publicly available encoders from Metasploit repository and trying to understand what exactly their whole algo is during the encoding and decoding stuff. So let me just hand this over to Yash.
Yeah, I'm sorry. All right, guys. So I think based on the online format that we are facing as of now, we won't be having much of interaction with the crowd directly. But as we declared that this talk is very much targeted towards people who have some sort of who have gotten into the infosec industry, but are trying to maybe break through towards advanced topics and get towards maybe red teaming idea as well. So this slide essentially covers where we have common patterns where like anyone who gets into anything based around exploitation, they definitely have to deep dive into understanding the architecture first. So as you can see that any tutorial that you find online, it will be limited to these things, that like getting you aware about basic registers, how like a 32-bit works, how 64-bit works, and then luckily some actually deep dive into ARM as well. There are multiple specialized training available, but if our current crowd, I think we have around 20 people over here. If people have some experience in ARM registers, I am quite happy for you. I think you have started your journey towards the advanced topic. But I have some details that anything that we continue discussing in this talk, whatever we take and explain, take that with a pinch of salt when it comes to ARM. That's why we have marked some asterisks over here, because the way these registers behave, not just on general ARM architecture, but all the variations and with extensions, you have to be careful about how you build your position independent shellcode. All right, so moving, okay, I remote access. Yeah. Is it okay?
Could you confirm?
I just got it. Can you switch to my phone? Yeah, perfect. So basic bread and butter for any operation on hardware for those based on operations, the encoder or direct shellcode. These are your general category of mnemonics which will always exist. There will be difference in how you handle your call and return as per your compiler design, but there will be some variations for your stack movements as well, because ARM will have its own register to handle linkage calls. So again, like, you have to consider some topics with a pinch of salt. You need to be aware of how non-standard operations might happen and how we will modify those. Next, please. Okay, so if you can view this, this will be like a very common trend. When if you have come across the tools like framework, you hardly will find any instruction which actually exists outside the realm of any generic tutorial. Like, you might find details where you will be in one specific instruction which is sort of new for you. But when you are either building your shellcode on your own or trying to use Metasploit for very basic operations, be it stager or different category of pillars, you will still be in the same realm. So the first diagram itself is towards 32-bit. The middle one is 64-bit, and the more garbled one, which is not even full, is actually the ARM one. So you don't have to focus much on the ARM diagram over here, because again, like, this might seem very simple, but these are direct explanation how your shellcode might look, and these are the views given by object dump tool. But we'll discuss down the line that how even your tools face issues while decoding these things. Next. Okay, so now you can see that even if we are utilizing very, very basic shellcode encoders where provided by tools, again, I think this is an example from Metasploit. So now your distribution starts changing outside your tutorial, like wherever you have worked on standard behavior of shellcode, like, okay, I'm writing a very position independent, direct focused shellcode, so I don't have to worry about operations which I'm not fully aware of. But until unless you deep dive into how an assembly program works, you might not even come across situations which might be handy for general applications, but not shellcode. So these are some operations which are provided with encoders because they tend to optimize for certain tricks. If you focus on the line, I think the fifth line, the scat opcode, and then there is the INS opcode, and over here C move GE. This is a conditional move, and then there is move AVS, which is again performing a packed movement. So in the flow, generally, like, you try to follow into very beginner level tutorials or topics, you will figure out that, okay, I know something, but I'm not aware of how things are happening. But that is how you actually switch into more advanced topics, by reversing all these failures. So this is a very simple example. Like, we are using, I think, XOR family, which is, the left one is a very basic XOR operation, and the right one is, I think, XOR dynamic. So these look very simple as of now. Next. Okay, so now when we start shifting into encoders which are provided by Metasploit itself, now as we see the behavior that Shikata-Ganai itself is a feedback, it's a feedback polymorphic encoder, and non-alpha is a table-based one. They sort of, in direction, do achieve you can say a polymorphic approach. Katakana is considered to be the excellent one, but the non-alpha is not. Despite the rating provided by the tool, you have to be very peculiar about your use case. How are you actually applying these? Because in systems, in realistic use, even though that these might feel that they are very simple, or they show as a very low rating or low ranking, they still function pretty well. Even certain high-end endpoint detection systems were not able to detect these. So why we are focusing on the behavior of encoders is because every time you start adding a layer of encoders, you figure out that whatever you have learned as an independent research or at the beginner stage, you will continuously be introduced with new and new instructions. So at this stage, as you can see, the non-alpha now has added RepNZ and JECXZ, SBB, and here Katakana is altogether a very new game, new ball for multiple people like FNSC, ENV, SPMove, and maybe push F also might be new for people who are just new to the whole exploitation category. Next. So in previous diagrams, there were scenarios where we did do inline packing of data, or we provided data which has to be somewhat positional independent, how shellcoders work, because we don't have any source or any approach where we can just inject any constant data in our runtime while we are exploiting. But we do need to find ways where we are able to do that as immediate value for the instruction. So not every tool will be able to decode that for you properly. We have had instances where packed data itself was interpreted as bad instruction. And in some cases, it could not even recognize between architectures if you go more towards a more polyglot approach. So here, I've mentioned pretty basic things which people can actually focus on if you're trying to move into the intermediate stage. If you're using any of these tools, I think from top to bottom, you're sort of going in the right direction, because any basic tutorial will cover object dump for you. And generally, this tool is a very simple tool. So it gives you whatever you provide as segments and essentially instruction section. It will perform a linear sweep for you. You can have a simple object code itself, not even a full binary, and it will still do a decoding for you. But the linear sweep itself does not guarantee that you will get correct output from that. Apart from that, IDA, Binary Ninja, and Gedra, be it in sophistication or being it new tools, these have come up and taken over the industry somehow, but they all follow somewhat on the lines of graph pattern. So these are pretty good tools. Like someone who is trying to get into this industry, they definitely need to understand at least one of them properly. And they tend to behave and work better than how object dump will help you in this learning curve. So one thing which is very common that we are actually considering cross compilation as one of the possible output, like one of the possible options to bypass endpoint systems. This trick very 10-year-old, but it still is pretty magical, like how it functions. This oddball case that we have faced very commonly is if you use GCC and multi-live with trying to cross-compile the data with -M32, or you use IC86 already cross-ported compiler already, it does give you a different output. You will have very similar instructions for majority of the data movement, but when you have calling in terms of tables, arrays, or any jump callback, these two actually give you different output. So if you're facing a scenario where one of your payloads or shellcode is actually getting detected, you can actually intermix these as well. Okay, going towards common methods, these are basic tricks which were actually quite helpful, going towards the idea where a very known old tool, PE Scrambler, this was, I don't know how it functions well now, because where tools where ML artifacts are available, where they are trying to run multiple cases based around your single binary and trying to figure out all the data path flows for any malware. This has given us actually good results, even in the unknown, like very small use cases. And one of the critical ones, which no one actually discusses, is tables. If you start reversing any of the known malwares, decent malwares, everyone knows that any known endpoint detection system or antivirus will have a very specific detection for hooking. This trick can be very helpful if you're using just shellcode bypass, or you're using bypass for entire binary or porting your own payload altogether. Jump tables is a very specific tiny tool where you just develop an index table or something similar to PLT or GOT for your own binary, where you can just say, okay, these are my parameters, and this callback looks very similar, and it performs an indirection inside. So many endpoint detection systems actually fail on the first table itself. Okay, so we were trying to figure out like what all other tools do we have at our hands. So I think, as we said, we have to redact a lot. So we had to remove Cobalt Strike from this. Cobalt Strike itself has very interesting features. And I think maybe if we are given the chance to come back to give training, maybe next year or some other talk, we will try to get that as well added. So we took broad category of payloads. Like we took the top 5, which are very commonly used for any basic use. These won't work for your red team approaches, but these are pretty good for basic BAPT and security analysis. So we took them. Sure. And we just did a frequency scan on the operations and how the behavior happens. So you will have very sophisticated tools available to you. If you're working with a team which does stock operations and handles infosec, and you have a data science team, they can actually give you a much fancy graph than this. This was a very shorty approach from our side, but this is what we have figured out, that if you take very basic payloads coming out from the standard tools or open source library, all right, yeah, we forgot to give shout out to Jonathan Salvan for this amazing Shellstorm database. This guy has blessed us for the last 10-15 years. I don't know how many tools, open source tools, actually utilize its payload in a very compressed manner. So the distribution in this graph is based around how many operations do you have which are based around register manipulation, data manipulation, or just generic categories. And these are pretty generic. Like we did some testing with Cobalt as well, but Cobalt has many more payloads or many more transport mutations available. So it slightly changes the graph, but we had to remove that data set from this. But this gives you a very known approach where you are able to figure out that your shellcode or your binary is pretty much similar to an existing payload or an existing normal binary as well, doing normal work. Next, please. Okay, so here you can see there's like a very slight change over here, but the way you have to know that is how these changes actually occur. Can you switch back and forth?
Yeah.
And back. So there's like a very slight change for people to understand, because we are trying to categorize this as just how operations function, not showing that how a specific change happened. But conceptually, when you start looking at layers, every time you add a layer of encoding or every time you add a layer of information, there will be some change or increase in certain type of operations. Because the next. Yeah. So here is like why and how we are figuring this out. Like, what was the specific change which we can't actually show you in graph? Major changes here, like if we add layers and branches, any more control and call changes will occur. But if we add any transformation where you are actually performing mutation on the data itself, be it you're overloading or just rechanging the data altogether, which is in the buffer, that gives you more data movement. This good example is any encoder which actually takes a stagnant section or a zone, maybe a payload which is loaded in memory, which is fully encrypted, or maybe which is 1:1 encoded by a basic encoder like ROT13. That essentially leads to a lot of data movement, because now you're trying to reference a data from some variable and it's still performing that operation in loop. So that continuously changes. And these might seem that, okay, these are simple, but how does this affect when we are saying that it's a very optimized shellcode? It's small, but it's performing looping. So there are subtle differences where we definitely will feel issues that, you have added loop, then there will be a change in graph. But if you have done loop unrolling and you explicitly try to have a new shellcode which works linearly, then obviously you will feel even more data movements are happening. So I think we forgot to mention this. But
yeah, please say that.
Yeah, okay. So in the last year, we forgot to add like a lot of screenshots, because every time you add an encoder, there are more than 30 encoders which are supported by some tools. So just to give you an idea that how you are shifting from the traditional registers and data operations, you're moving towards obscure ones. These are the ones which multiple people miss out, who are just into industry but are not getting comfortable with performing in-depth analysis, or even are not comfortable with actually coding the system out. So these are some common things that we found out, while like some common mnemonics which we found out. These are very less, but you can definitely find a few more. We haven't even added the Shikata Ganai one. Actually, we skipped Shikata Ganai. It's like a brainchild from the original author, and if you want to have a deep dive on it, I think you have a ton of resources available online, because that is one encoder which has been ripped apart from multiple researchers. You'll definitely find interesting use cases around that. So apart from that, what are the good techniques which we are considering? So these are generally frowned upon: MMX, SSE, AVX, any type of SIMD, SIID operations, because people feel that if your shellcode is not hardware independent, then how will it function? Like we are not living in 90s. We have crossed 2000s, 2010. Nearly any hardware which you have after Pentium, it definitely does support this. It's an exception for how you handle the case for ARM, but it's definitely like you can actually utilize this. We do have a case study on how we are using encrypted shellcodes, where we do utilize the registers which are available part of these extensions. Next.
So regarding obscure mnemonics, so when we are talking about Repni's CASB, so these opcodes, we actually was going through, code from Metasploit encoders section itself. And from there itself, we found some certain uncommon used opcodes that was utilized to perform encoding and decoding part. So of course, these opcodes were a part of decoder stub itself. But now that we are talking about encoding and decoding, so my generic question to actually everyone of you is like, why do we need encoders? Like, can't we just use raw encoders, raw shellcodes directly in memory and run that to get maybe a reverse shell or maybe perform any kind of operation, right? So I know this kind of a noobish question, but again, everyone needs to like literally have to understand one point, that the time when Shikata Ganai was introduced, and at that time any kind of obfuscation that was done, any kind of encoding and decoding that was done, that was solely and heavily dependent on Shikata Ganai. And most of the threat actors and pen testers and even red teamers at that time also, they were kind of focusing just on bypassing antivirus solutions via just encoding encoding their shellcode with Shikata Ganai. Obviously, at that time, most of the people, they were kind of using Metasploit as their first choice of tool and framework, right? But now that Shikata Ganai itself has been, properly dissected and analyzed, by all these security vendor companies. So they all have signatures for Shikata Ganai itself. So there's no point in you just use a Shikata Ganai encoder on your shellcode to encode and to try to bypass some of these next gen antivirus solutions and security solutions. But even if you modify a little bit of how the whole process works, that could actually help us out, right? So again, now coming back to the question, why do we encode itself? So the most important part of encoding itself is, like, yes, we can transform the shell code, right? It can be, let's say there's a web application and let's say there's a web application with buffer overflow vulnerability in it, right? And yes, there is a firewall in place just before the web application. So just directly putting up the shell code, you can't expect that shell code to run, right? Because you still have to perform some kind of encoding decoding mechanism, right? What I'm talking about is Unicode based encoding. So web applications, they won't really, most of the web applications, they won't really accept just direct encoders, sorry, direct shell codes when you generate from maybe from your tool, your implant, or maybe, you know, if you're using Metasploit. So at that time, what you do, the shell code itself, you have to modify, you have to change the shell code, transform the shell code into a Unicode, right? So that it can be accepted by a web application when it passes the shell code from web application to internal mechanism, when it processes that shell code. So the instructions should be easily mapped out on the memory region. So that's why encoding is necessary. Yes, I do strongly say that. And when we are talking about bad characters, so yes, many of us may have, you know, done OSCP certifications and a lot of different certifications. And even in real-time scenarios, you guys may have encountered some situations where you are, you know, trying to run your shell code on a remote machine, but your shell code is kind of breaking on that machine, but it's running on your machine itself. So what could be the reason? You know, what exactly is the missing part here? So that's what we are focusing on, just replacing the bad char in the shellcode itself. Of course, bad char itself is an ongoing process. You just have to select, you just have to analyze what kind of bad chars are there, and you just encode so that those bad chars are not repetitive and are not represented in the shellcode anymore. So that's another aspect, a plus point of adding encoder part. Now, if you are now just for the information, like when we are when the shellcode is stored in memory, right? So by default, so shellcode itself is neither good neither bad, right? Because until or unless the shellcode is called by a function and the memory region is set to execute, if the permission is set to execute, then only antivirus and you know, other security solutions, they'll find this as an anomaly and they'll detect this, and they'll based on the detection, based on the signature, they'll detect what kind of you know, shellcode execution is happening, right? But if you just use the same shellcode and just copy it into buffer and that's it, you don't do anything, you don't call the shellcode, you don't run the shellcode, so it won't get detected itself. Reason being, again, because it wasn't executed at that time. So but when we are talking about execution of the shellcode, so at that time itself, so all kind of detection happens. So when you encode the shellcode during the encoding decoding mechanism itself, so at that time, you know, you can there are some methods that you can utilize to defeat these kind of detection mechanisms. So again, from a very basic scale, how does encoding decoding process work actually? So we have the stub, right? We have the raw shell code, and what we do is we encode the shell code to generate encoded shell code itself. But at the same time, we also add a decoder stub to it. Decoder and encoded shell code, they gets when we inject or maybe copy the whole shell code or encrypted shell code with, sorry, encoded shell code with decoder stub. So when we copy this to the memory itself, the first things first, decoder stub will start decoding the shellcode, and that's how the instructions starts to execute. Right, but there is one more important thing, that there are some issues that may arise during the shellcode execution at that time. So in case we don't have any kind of, in case we don't have any kind of memory space available to add a full shellcode itself, sometimes, you are using, let's say, a stageless stageless shellcode during maybe an engagement or pen testing. So at that time, it's highly possible that the shellcode itself might break, because it might overwrite the bytes to nearby regions itself. So when it's decoding, so that's why it's always a good idea to add a NOP sled before and after your decoding stub, and after the encoded shellcode, so that it can have enough space to provide the decoding mechanism itself. Now, when we are talking about decoding mechanism of shellcode in memory, so at that time we definitely need to have permissions to it, otherwise it won't directly work. Of course, there are some issues, like, let's say, if this NX bit, okay, and ASLR and all that is enabled, so at that time you can't just directly execute the shellcode, so you have to find another way, which is definitely, like, these techniques are so much popular now and easily available online, how to bypass NX bit and how to bypass stack canaries and ASLR bypass and all that. So
I'm sorry, you have to conclude quite soon, because you just have 1 minute left.
Yeah.
Thank you.
Okay. So yeah, let me just go quick then. So now the issue is when we are adding the decoder stub itself in memory. So decoder stub itself has a pattern, right? And that's how antivirus and other security products, they kind of detect the decoder stub. So based on the pattern, so they detect what kind of decoder it is being used, and is it a threat or not. Now that's why it's a good idea if you just kind of obfuscate the decoder stub itself. That's why instead of encoder and decoder, we can definitely move along towards encryption part itself, because encryption will provide a little bit more a better approach towards encoding, decoding, but at the same time it also covers the morphism aspect and a mutated aspect of encoders. So when we are talking about basic encoders, right? So basic encoders, it's a one-to-one map, and morphism, we have polymorphism, metamorphism. So for polymorphism, you can definitely check out Shikata Ganai code is good enough to understand what excellent encoder it is based on how it generates dynamic XOR keys. Now, for mutated and polyglot, so like I said, all these encoders can also be a part under encryption. So all we need to just focus on is using encryption in encoding mechanism. So these are some of the common encoders that we can think of, and they're commonly used, especially Shikata Ganai and Blow XOR. So that's also there in Metasploit, and definitely a good to go one. Now, also, we also have for 64-bit, we also have there's another encoder, Zutto Dekiru. That's another encoder that was quite amazing, I would say, because when I used it in my engagement itself, so at that time we used Zutto Dekiru to encode the SMB based payload, because we used Mythic C2, so at that time we definitely utilized that for that purpose. So we have some case studies, so we don't have much time, so we'll be like quickly moving forward. So for case studies, we have NOP generators. We don't have to just rely on the the 90 \x90 opcode itself, what we can do is we can definitely utilize some other knob generators which doesn't include 90 itself. So Metasploit have that, and we have definitely utilized this, and it gives custom and knob generator just before your encoded and encrypted shellcode, and then comes the encrypted shellcode, and then you have you give just a little bit more NOPs. That should be good enough. And static bypass are easily available that way. Bypass are easily possible that way. But when we are talking about behavioral bypasses, that is not we are covering right now. But when we are talking about AES encryption, hardware level encryption, so that can definitely bypass the behavioral part. So we have Xanax encoding, thanks to Alan, who provided Xanax encoding, and the whole idea itself it's pretty clear, and it's just that the key is hard coded, as this is just a POC, and we can definitely modify this accordingly. So we have the Xanax encoding, we have the decoding part, and after that actually comes up with alpha upper encoder. That is quite amazing. Yes.
I'm really sorry, but you have to finish very soon because we are supposed to start the next presentation now.
Oh, okay. Sorry, we didn't get to the.
All right. Okay, so do you want us to conclude on that? Cedric, can you hear me?
What?
Do you want us to just conclude with a statement, or do we have a few minutes?
We don't have more time left, so I can give you 1 minute more, but no, not anymore on the weekend.
All right. So what I'll do is I'll just summarize the last thing. So essentially, the last encoders that we are actually showing as case studies, it's pretty interesting for people to realize that whenever you are highly dependent on tools that you have, which are commercial or open source tools, they might not yield the same behavior as you expect. And the case study that we have mentioned for these four, these were something that we have regularly used and figured out that, okay, even though that these are open source, but not in the limelight, they have performed pretty well. And AES-NI is something that we are sort of trying to venture into, because to be able to generate a position independent shellcode for this or make it compacted, this takes time, but this is modern and essential for people who want to actually get into some features which are highly polymorphic. But I won't say that this is like a single cannon shotgun approach where it solves everything for you. Can we just skip 2 slides? I think we'll read later. More problems. On the pitfalls. Yeah, so from here, I'll just summarize these. So once you actually read through a slide and you figure out what do we do? So it does guarantee, because see, AES itself gives you that you have a polymorphic always, but it does not guarantee a bad car issue because it's dependent on its cycle. Sometimes there will still be issues that you will reach bad car. So you might need to add your own encoding there as well. But that's like a new research we are trying to venture into. Some tools do provide it. We have added a slide on that. Metasploit framework provides AES at software level, but it's essentially utilizing the older registers itself, not using the hardware accelerated one. So this is something that you try out integrating in your tool, because till the time companies will catch up generating Yara tools, this will still give you a pretty good success rate. Be it on modern devices, M1, I think you can look into Neon and Helium intrinsic support. These are the extensions for ARM, where you can develop into, you can convert these shellcodes into it. And the final case is the ROP chain. Like if you have an application which is already utilizing these instructions and you can build a ROP chain around it. This is very bleeding edge. We are trying to pull off something around it. It can be something that our viewers can also look at. And one thing that people can have issues facing over here is whether your shellcode gets flagged as a ransomware or to the instructions to a ransomware. So I think we can conclude here if we don't have time. Thank you.
Thank you, guys.
Thank you.
Okay, thanks very much for your presentation. So we don't have some time for a question. I propose to start the next one. So the next presentation is from Thomas Rakiki, and it's about timer in Navigator in browser in order to run time-based attack. So Thomas, you can start by sharing the screen. That's perfect. Thank you.
Okay, thank you for the introduction, and sorry for interrupting your talk, guys. It was really interesting. So I'm Thomas, and I'm a PhD student in Rennes, and today I'll present you a paper called In Search of Lost Time, a review of JavaScript timers in browsers. So this was joint work with Clémentine Maurice and Pierre Laperdrie, who are both researchers in Lille, actually. To give you a little bit of context, my thesis focuses on JavaScript timing attacks in general. So it's a pretty wide subject, but the important word here is timing, because we exploit subtle timing differences to infer secrets from the JavaScript sandbox. So they could be password, they could be data, they could be browsing history, whatever. Everything we shouldn't be able to get from the JavaScript sandbox, we call it a secret. So to mount most of these attacks, we need timers with a really high resolution. In general, we need a resolution of at best 10 to 100 nanoseconds, so that's very small. So do we have that in JavaScript? That is the first question we ask ourselves. But the answer is a bit more complicated than that, because here you can see the evolution of the resolution of performance.no, which is the highest resolution built-in timers available in browsers JavaScript. As you can see, for Chrome and Firefox, it has changed almost 10 times over the last few years. And every time with different values, ranging from microsecond to millisecond. It's a bit chaotic. Clearly, the changes are reactions to timing attacks. But our question was, what are the security implications of, well, all these changes in timers? Because we have values, browser vendors tell values, but we don't know what it really means. So to try and get a better view of this, we've established a classification of all JavaScript timing attacks. So we've isolated 4 major classes, each time with prerequisites and properties. And our idea with that is if you know the prerequisite to a certain class of attack, you can prevent this certain class of attack with more ease. So the first class we've isolated is hardware contention-based attacks. So here, the attacker infers secret from timing differences that are caused by different hardware states. So for instance, the cache can cause different timings for the same computations. But you can also attack the DRAM. You can attack pretty much everything with that. So to mount them in JavaScript, you need high-resolution timers, of course, but you also need shared hardware resources. And when I say shared, I say shared between the JavaScript sandbox, so a restricted environment where we run our code, and other victim processes on the victim's machine. The second family is probably the cool kid at the bench. It's transient execution attacks. You've probably heard a lot of it recently. But here, the attacker infers secret from traces of transient execution on the hardware. So to simplify, transient execution can be out-of-order execution or speculative execution for Spectre. So Spectre, notably, is the most famous attack of this class. But even Spectre has many different variants, and there are other attacks with each time different properties. But one common prerequisite for transient execution attacks in JavaScript are, well, transient execution, of course, but you also need a hardware covered channel, generally a cache covered channel, to extract the data. So you need the same prerequisites as before, which are high resolution timers and shared hardware resources. The third attack is more software based, so third class, sorry. Here we exploit timing differences caused by operating system level phenomena. For instance, system interruptions or memory deduplication and many others. So here we need, logically, you're starting to get hit, high resolution timer and shared system resources. And the highest level of timing attacks we have isolated are attacks based on browser resources. This time we only focus on attacks based on, well, for instance, browsing history or shared extensions in the browser or event loop, if you're a bit familiar with how browsers work. So to mount them, we need high resolution timer and shared browser resources. So I think you got it, but there is one common prerequisite to all these classes of timing attacks, and logically, that is high resolution timer. So let's focus on timers in JavaScript a little bit, because it's not as simple as it looks. I've mentioned it before, we have one high-resolution built-in timer in JavaScript, which is called performance.now, because it was used to evaluate websites' performance. But its resolution at this point in time ranges from 5 microseconds to 1 millisecond. That's already good, but it's highly insufficient to mount timing attacks, because remember, we need a resolution ranging from 10 to 100 nanoseconds. And we cannot measure that with performance.now. So how do we do that? Because here you can see we have two events, event 1 and event 2. And to mount a really bad attack, we need to distinguish them. And clearly here, the dashed line represents the clock period. So here is a tick, here is a tick. If we measure both events will have a 0 execution time, and we cannot distinguish them. So what we do, we use something that is called performance.now interpolation, or clock interpolation in general. We take a small constant time operation, and we execute our event at the beginning of the clock period, and then we run our short constant time operation. We call it a tick. In general, it's a variable increment until the end of the period. So what we do basically is, instead of measuring the time from here to here, do you see my cursor? I'm sorry, I'm not sure. I think so.
Yeah, yes, that's okay.
You don't measure time from the beginning of the event to the end of the event. You actually measure the time from the end of the event until the end of the clock period. But since you know the duration of the clock period, it's basically the same. So here we can see that the interpolated time is of 7 ticks. For event 2, the interpolated time is of 5 ticks. So hooray, even with our bad resolution timer, we can distinguish both events. And that is really cool, because it grants us a resolution that is naively the duration of the tick, so the duration of an incrementation. So it's really, really fast. It's nanosecond accurate, actually. A few things you need to know about this timer is just facts that may be useful for the following of the talk. So you actually measure the time between the end of the event and the end of the clock period. So it's the longer the event, the shorter the interpolated time will be. So all the graphs are backwards, but that's a detail. The really important thing to remember here is that whatever the duration of the event is, you will need a full clock period in order to measure it. Because here event 2 is longer than event 1, but you still need a full period to measure. Another very interesting auxiliary timer is based on shared memory and shared array buffers. So the name shared array buffer is pretty explicit. It's an array that you share between your main thread and a subthread. And it's actually part of the evolution of JavaScript towards a more multi-threaded path, a more dynamic path, because websites are getting more and more complicated. So to build a clock with it is really quite simple. Our main thread that wants to time event 1, we create a clock thread and share a shared array buffer with it. The only purpose in life of the clock thread is to increment a value in the shared array buffer all the time until we tell it to stop. And since this incrementation is constant time and small operation, we can use the value in the shared array buffer as a timestamp. So the main thread just has to check the value before and after the event, and it will know the duration of event 1 as a multiple of the ticks. So we still have a resolution similar to performance.now interpolation. That is more or less an incrementation. So this means that we have very basically very powerful timers in browsers if we don't take more timing-based countermeasures. Because we've seen that reducing the resolution of built-in timers is not sufficient. Even if we have a resolution of 1 hour on performance.now, we'll still be able to interpolate it. It will just take longer for each timing measurement. So what browser vendors did, I think it was in 2018, it's one of the most popular timing-based countermeasure, is to add jitter to the measurement, which is basically each tick, instead of lasting 1 second, for instance, will last something from 0 to 2 seconds. So basically, we have longer ticks and shorter ticks. Well, longer clock periods and shorter clock periods. They added jitter to all timing sources in JavaScript. And yeah, that is very efficient because for clock interpolation, 2 events that have the same duration, here event 1, well, and event 1, will have different interpolated time because we measure the differences in time between the end of event 1 and the end of the clock period. So if the end of the clock period moves, we don't have a reliable timing. So this was very efficient and elegant. So they implemented it in 2018, just after the publication of Spectre. So Firefox set a resolution of 1 millisecond with jitter and Chrome of 100 100 microseconds of jitter. So at this point, the timing-based countermeasures were the harshest in the short history of timing attacks. So this is a really elegant solution. And what did they do for shared array buffer? Because they also pose a really big threat. They found a very nice solution and simple of just disabling them. So they disabled them just after the publication of Spectre, so in 2018. So that's it. That's the highest point in timing-based security. But this raised the classical question in cybersecurity of security versus practicality. Because, well, high-resolution timers are here for a reason, because they are very practical for web developers. They are here for performance measurements, of course, I've mentioned it before, but even for animation. Because if you have a 60 frame per second CSS animation with a 1 millisecond jitter on it, I can guarantee you that you will see it and the animation will be a bit ugly and a bit jittery. And shared array buffer, especially, they are really important part of the evolution of the web to a more complex, dynamic websites. So it's a really important tool for the evolution of browsers. So web developers weren't happy, and browser vendors wanted to react with more efficient and less penalizing countermeasures. So if you remember correctly, another common prerequisite for all timing attacks was shared something resources. The only thing that varied was shared hardware resources or shared system resources, for instance. But this means that instead of having timing-based countermeasures, browser vendors could add more isolation in order to not have shared resources. And that is the case of the second big family of countermeasures, which are isolation-based countermeasures. Even though you can apply that isolation at many different levels, it was at the operating system, at the software level, that the most notable propositions were made. In particular, site isolation has a very simple principle. Each site in your browser runs in a different process. It's that simple, but it grants a lot of isolation at the process level, because you have different address spaces, you have different PID, many things are different. And even if the idea is simple, the implementing it was really hard for browser vendors because it required major architectural change to browsers. So Google Chrome released it, I think, well, in 2019, but Firefox released it only a few months ago, actually. It was Project Fission. It's really good that they released it, but it required major work. Another similar countermeasure is called kubectl. It's a bit formal, it's a bit complicated, but what interests us here is that it's mainly a set of HTTP headers between the top level domain and all resources that are loaded in the website. And if every resource agrees on a shared policy, well, the group becomes cross-origin isolated, that's what they call it, and it becomes its own process. What is important to note about that, and on contrary to site isolation, it's not activated by default on all websites. If you go on Google right now, it will not be activated because it's a responsibility of every website to implement it for their own website. But this also means that if an attacker controls the website, it can activate or deactivate kubectl as it wishes. So let me be clear for a minute about the goal of isolation, because I think, according to me, that is where this whole issue stems from. Different processes mean different address spaces. It's that simple, but it's really good because it prevents all attacks that target a single address space. Mainly, and that's why they implemented site isolation, mainly it prevents Spectre v1, so the first publicated version of Spectre. So that's good, and that's a really good, not publicity stunt, but it's really good to prevent Spectre because it was really threatful. But I want to be clear on what it does not prevent. And it's by design. They don't claim it prevent it. It's just there's a bit of confusion. It doesn't prevent hardware contention timing attacks. So all cache attacks are not prevented. And that is logical because hardware is situated below the security rings of the operating system and processes and blah, blah, blah. But it's, that's ugly. It also does not prevent cross-address space transit execution attacks. Well, all cross-address space attacks, but including a whole other category of transaction attacks. Some Spectre attacks, not V1, but other, can actually target other address spaces, or Radel can also attack other address spaces. So for instance, just to give you an example, right after the publication of our paper, Google released a leaky page, which is a really cool demonstration of a transaction execution attack in the browser. I highly recommend you check it out because it's really nice, it's really neat. And yeah, that's it. But these isolation-based countermeasures brought a change in defense paradigm against timing attacks. Because with the introduction of site isolation in group web, browser vendors fixed Spectre. So they consider the main security issue fixed. So there is no reason to bother with the old penalizing heavy timing countermeasures. So they reload access to high resolution timers, so microsecond accurate timers, and access to shared array buffer. That is only when QAP is enabled, because we need to be in a secured environment. But still, no analytical control websites, you can have access to high resolution timers with very small jitter and access to shared array buffer. So the impact of these changes is quite unclear because timing-based countermeasures are efficient against most timing attacks. And I want to insist on the genericity of timing-based countermeasures because even future 0 days that are timing attacks can be mitigated by timing-based countermeasures. And that is not the case of these new isolation-based countermeasures, which are really strong and really efficient, but they only focus on a small subset of all the timing attacks. So currently at this point in time, hardware-based timing attacks and many other transaction attacks or software attacks, whatever, are only mitigated by timing-based countermeasures. And with browser vendors a few years ago, well, 2 years ago, I know I'd say, just softened the timing-based countermeasures. So, and the softening of countermeasures was not really properly evaluated. They just say, this value is a new value of your resolution, and we don't know much about why this value and what it means in terms of actual security. So our question was, what are the security implications really of setting these high resolution timers? Let me just drink for a while. So to answer this and to provide a more reliable evaluation, just to say it's bad, we built an automated framework to evaluate JavaScript timers by using Python and Selenium, so we could actually automate browsing and running on experiments. So it currently only works on Chrome and Firefox and some, well, Chrome and Firefox-based browsers, including past versions, and also hopefully with minor change, future version. Because our goal with that is that our analysis is not just at this point in time of 7th of July, but it can be more durable and more helpful even in the close future. At any point in time, we can know what is the state of timer security in browsers. You can find the code on my GitHub or more detailed explanations about the architecture in the full paper. So you may wonder, how do we evaluate the timer? Well, our framework focuses on two major properties. The first one being, of course, the resolution. It's quite obvious. To simplify it, it's basically the smallest operation timer can measure. So if we have a really bad resolution, we cannot measure really precise events. But the second property is a bit less obvious and a bit less naive. It's we call it measurement overhead. It's hard to explain, but the time it takes to make the measurements, but it can be independent of the duration of the timed events. For instance, if you have a stopwatch, the measurement overhead would be the time it takes to click before and after the timed event on your watch. I say it's different than the time of the execution time of the timed event, because here for performance.net interpolation, I've said it before, we need a full clock period in order to do one measurement time, one measurement. This means that even if we measure an operation that lasts 2 nanoseconds, we need a full millisecond in order to measure it on Firefox without CoAP. That may seem like a detail to you, but it's actually really important because to mount cache attacks, for instance, we need hundreds of thousands of timing measurements. So this would require hours if we need a millisecond to measure time once. And we don't have that on a web-based threat model, because on average, an attacker, a user will stay a few minutes on a website, not more, even more if his CPU is blowing like crazy. So the duration time of the attack is really important. So the measurement overhead is really, really important. So let's evaluate both timers under these two criteria. So the measurement overhead for performance.net interpolation is quite simple. it's on average the resolution of performance.now. Keep in mind, it changes because of the jitter, but on average, it's the resolution of performance.now. The resolution, on contrary, is really hard to evaluate because, well, still because of the jitter. Because of the random values, we cannot really evaluate the smallest operation we can measure. So we did kind of a weird trick to know the resolution of our timers. We took a problem we know very well the resolution we need to mount. So cache attacks. We know that we need a 10 to 100 nanosecond to mount cache attacks. And we said with the timer, if we can mount cache attacks, this means we have a sufficient resolution. So do we have, for cache attacks, I won't get into heavy details, but basically we need to distinguish whenever you call an address, if it's served from the cache, so a quick access, or if it's served from the DRAM, so a slower access. So we have two distributions and we need to be able to distinguish them. So do we have that? This is for Chrome 84. So clearly, you can see on the orange are cache miss and on green are cache hits. So you can distinguish a bit the two distributions, because here you can see that these are faster, not slower because it's inverted, and these are faster. But still, we have something like a 30% error rate to distinguish both. So this is really not sufficient to mount cache timing attacks. 30% error rate is really bad. So with just a single measurement, we don't have a sufficient resolution. So we don't have the 10 to 100 nanosecond resolution we wish to have. So our idea comes from how the jitter is computed. It's basically a triangle distribution around the real value of the resolution. But if we repeat the measurement enough, it will reduce the randomness, because on average, the clock period will start to get closer to the real value of the resolution. So increasing repetition lowers error rates, but logically, it increases the measurement time. If we do 2 repetition, it will double the measurement time, etc., etc. So it's all time precision compromise with this timer, because we don't want to have a too high measurement overhead. So you can see that the error rate drops logarithmically with the number of repetitions. So we've set an arbitrary 5% error rate, because with 5% error rate, we can mount cache attacks. And we say, so for instance, for Chrome 84, with I think it's 7 repetitions, we can mount cache attacks. So we have a 10 to 100 nanosecond resolution. So it was 8, sorry, not 7. But this means that for different browsers, we have a different number of repetition and a different base resolution, which means the measurement overhead varies a lot. And specifically for Firefox without kubectl, so that is similar to timing security 2 years ago. To do a single measurement with this high resolution, we need 18 milliseconds. That is huge, because compared to Firefox 88 and Chrome 90, we only need 40 microseconds. So we are already 3 orders of magnitude below. But that is nothing compared to shell array buffer, because here we don't have jitter, so it's really efficient. The resolution is basically the time of an incrementation in the shell array buffer, so somewhere around 10 nanoseconds. And the measurement overhead is twice the time of a read, so 20 nanoseconds. It's just like with a stopwatch, click, click. All these numbers are quite abstract, so I want to give you a concrete example about their meaning, because we don't really know what 12 nanoseconds compared to 40 microseconds means. But with this example, it's still a bit theoretical, but an ideal bit rate, if we were to build a cache covered channel, so we have 2 browsers on the same machine or on the same Amazon shared machine that want to communicate with one another through the cache. So by sending cache hits, they send a 1, and by sending cache misses, they send a 0. If they want to communicate, they would be limited by the measurement time, because each bit is 1 time measurement, among other things. So we have an ideal maximum bit rate to get for this covered channel. So for Firefox 88 without kubectl, so that's similar to 2 years ago, so harsh timing restrictions, we have at best, and keep in mind it's at best, a 60 bit per second bit rate. But on Firefox 88 with kubectl or Chrome 90, so on US versions on the packet control website, we get 200 kilobit per second. So we already have 4 order of magnitude difference between these 2 values. So with the softening of timing-based countermeasures. And for shared array buffers, we actually have 50 megabit per second ideal bit rate. That is huge for a coverage channel. Of course, we couldn't build a coverage channel with such a resolution because there are other factors that take into account, but still, we are 6 orders of magnitude in difference between 2 years ago and right now. Another cool example, I think, is building an eviction set. I won't get into the details of what an eviction set is or how to build it, but keep in mind that it's a prerequisite for most cache attacks on JavaScript, and you need to run it on the victim's machine before running your attack. So each time the attacker visits the seat, you need to compute the eviction set before running your attack. And it requires a number of time measurements that is proportional to the number of cache lines. So this is a very more concrete example because we've run the code actually. And on Firefox 88 without CopCop, we need 10 minutes to mount this eviction set. But with the new timing based countermeasures, we only need 50 seconds. So it's already more acceptable on a web-based model. It's still a little bit high, but it's okay. But for the shader buffer, we can mount it in just under a second. That is really threatful. And to give you some perspective, because I like giving this number, on Firefox 88 on an attacker-controlled website, the attacker can create a coverage channel with a bandwidth that is 800,000 times superior compared to Firefox 78, so in 2018. And it can also compute an eviction set in a matter of seconds, whereas it required tens of minutes before. To put it simply, even if you didn't understand the example, timers are really more threatful than 2 years ago. Really, really more threatful. Oops, sorry, I just keep hitting my computer. To conclude real quick, at this point in time, today, powerful and fast timers with a really high resolution, you can mount powerful attack, transaction attack with. They exist in your browser. We can create them. They are not built in, but it's easy to build them. And the new isolation-based countermeasures that was released by browsers are really good against Spectre. So you're safe against Spectre v1 and some other system resources, but you are not safe against, well, all the rest of timing attacks because we have these powerful timers. This means that all previous attacks discovered in the literature and many others are available, but also future zero-day timing attacks. Well, they are free to come because timing security is really weak is a bad word, but it's really at a strange place because it's too penalizing. So as usual in cybersecurity, the general conclusion is, well, you need to find better countermeasures that are less penalizing than timing-based countermeasures and that are more generic, that apply to all timing attacks. So more generic than isolation-based countermeasures. But the thing is, it's starting to get a bit out of the browser jobs to fix that because they cannot fix hardware issues or transaction issues, and they don't have that much control at the operating system level. So, well, we don't know what to do if we should remove these high resolution timers because it's really penalizing. But just having them right now, we just wanted to underline the risk that it represented. So thank you for your attention. If you have any questions, you can, well, ask them in the Q&A or contact me. My mail is here. You can find more information and more technical details because this was very high level in the paper. And you can find my code here, our code. So that's a bit egoistic. Thank you.
Thank you.
Thank you very much.
Does anybody has a question? For me, all attacks you show are possible in every browser, or some browser try to implement some protection against such attack.
It really depends on the classes of attacks. For hardware-based attacks and transaction attacks, for instance, in general, with a few tweaks that can be hard to do, they can be implementable in most browsers because, well, browsers cannot do much about, well, the hardware. Actually, Google Chrome tried to release something against Spectre, but they lost something like 40% performance, so that was really bad. And for this type of attacks, no, sorry. it works on most browsers. But for more software-focused attacks, it really depends on the browsers because, well, mostly they handle their own resources. The architecture of the browser is not the same. So yeah, for lower level attack, it's really portable. For higher level, it's really more specific to the browser.
And what about mobile devices? There are same kind of issue with them?
Yeah, I'm actually not an expert of all the hardware of a phone, but just on timers and on web security, it's actually always been a step behind the laptop, the desktop security, to say. So this means that there were never been the hard countermeasures. Timers were always high resolution on phones. And I think they are trying to really, I don't want to say anything wrong here, but when we wrote the paper, site isolation was not released on the phones. Yeah, so it's even a bit worse. But I don't know the state of well, cache attacks and everything on phones because the architecture is really, really different.
Okay, thank you.
And maybe one more question.
Mm-hmm.
Have you tested other exotic browsers? Are there some that that are more aggressive towards security measures?
Yeah. Well, of course, as usual. Well, we've tested most popular websites, so all the Opera, Safari. Yeah, I think I don't remember the name of the Apple one, and Tor too. So as usual, Tor is kind of the best student because right now I think the resolution is of 100 milliseconds with a 100 millisecond jitter. So yeah, clearly they are really strict on timing-based countermeasures. So that I think a good thing, but it's not really practical as usual with Tor. So yeah, that is good for Tor, even though they only focus on well, timing-based security and the site isolation brought by Mozilla. I don't think there are many other countermeasures that are exclusive to Tor. I think it was a browser developed for Mac. I don't remember the name. Is it Safari? I think it is Safari. That has a different approach. We would have liked to extend the framework to it because each time the values in timing security are different, and they have a few other countermeasures that detailed, but still important to take into account. But since we didn't really have access to this material and we didn't have much time, it is not currently applicable on Safari, but we've evaluated specific versions, and it depends. They have, in general, they have a high resolution, but no jitter. So it's kind of a mixed feeling about that. But you should use Tor if you're scared of timing attacks, or maybe other open source browsers that are really strict on countermeasures. Yeah,
and I was wondering also if generally these if these attacks are tied to the processor architecture, or can they really occur on any architecture? Is the architecture part of the solution?
Yeah, I think so, because currently all the most of the attacks I'm focused on work mainly on Intel. But the thing is, because of differences in architecture, I don't think there is currently a safer architecture than another. It's just that, well, currently Intel is more attacked than the others because it's more popular. But small differences in the architecture, for instance, the cache inclusivity can bring great changes. So certain cache attacks are not implementable on AMD CPUs, for instance. But I don't think that's really a security per se. It's just a, well, there is no vulnerability because it's very different. So there are attacks that are exclusive to RAM, ARM, or AMD, for instance. But yeah, but most attacks I've mentioned here, so Spectre, for instance, is mainly focused on Intel.
Yeah, of course, for this one in particular. Okay, thank you. That's all for me.
Thank you so much. It was very nice. So we have a pause of 10 minutes, and we start at 4:10 p.m. See you.
Thank you. See you.
Okay, we will now have the last two talks for this edition of Pass the Salt. So this talk will be given by Niels Amiet and Tommaso Gagliardoni from Kudelski Security, and they will talk about a method to store data in a very untrusted environment. So you can share your screen. I guess you will be co-presenting.
Yes, thank you.
Tommaso, you are still muted. That's okay.
Yeah, sure.
Okay. Okay, so we have we can see the slides. It's all right.
Thank you. So hello, everyone. Today we will be talking about ORMFS, achieving storage agnostic privacy. So my name is Niels, and I'm on the research team at Kudelski Security, and I have interests in open source software, big data analytics, and modern programming languages. And today I'm also presenting with my colleague and good friend, Tommaso.
Thank you, Niels. So my name is Tommaso. I am also in the research team at Kudelski Security. I'm a cryptographer. My main interest space from the theoretical side, especially in the field of quantum security, to the more applied side, especially in the fields of anonymity and privacy. And this talk is actually pretty much about privacy because it is about the security of sensitive data at rest. So I will start with a quick introduction to the problem and to the issue of securing data on untrusted storage. So the typical scenario we are dealing here is when a user has some sensitive data that needs to be stored, but the storage medium is not trusted. Typical example we have, I don't know, you have an HR department of a big company. HR has a database of employee salary records, and this database is stored somewhere externally, maybe on some cloud. So clearly, this information is sensitive, and the cloud provider is not to be trusted. In other words, we don't want the cloud provider to have access to this data. We have to see the provider as an honest but curious adversary. So the typical solution here, pretty standard, we encrypt all the information. So HR has encryption, decryption key, and the whole database is encrypted on the cloud provider. So no passive adversary can read the content of the database. And so all is good and everything works fine. Well, not very much, otherwise we wouldn't be here giving this talk. Because even if the content of the database is encrypted, there is some information potentially leaking. For example, what if a new employee joins the company? By only analyzing the size of the encrypted database, you might see a new entry being added. What if an employee gets a raise of salary? You would see the corresponding encrypted field of the database changing. You cannot still access the underlying value, but you see some change, so you can infer some information. If an employee quits the company, you will see that the corresponding field will be reset, or it will not be used anymore for a long time. So in all these cases, some information leak, even if the content is encrypted. But that's not just a cloud problem. In fact, it's quite, it happens also in hardware, especially in the area of secure elements. So for example, here we have a smart card. And typical example is when a smart card needs to manage independent keys that are used for different access. And these keys are stored on some memory, but this main storage is also to be considered untrusted, because an external, tampering with the memory can reveal the keys. These keys can be read, analyzed, modified even. So again, this is a situation where you have a trusted environment that is trying to deal with sensitive data on untrusted storage. So again, here, something that is done in practice in many constructions of secure hardware is the following. You use a small but expensive area of trusted memory that is tamper-proof, it's resistant to analysis, and you store one single master key inside there. And you use this master key to encrypt the bulk external storage that can then be used to encrypt, can be used to store other keys. But again, a scenario like this also has a similar problem to the cloud scenario we saw before, because you can infer many information just by looking at how the encrypted storage changes. For example, you can see that a certain event triggers a certain key. You can infer that a key is needed to do something particular that can also be cross-referenced with offline information. So for example, you know that a certain door is the CEO's door, and therefore that key is used by the CEO. You can see when the key is updated, added, removed. So again, some information is leaking. Okay, now you might wonder, okay, but this is all on a theoretical level. Does it really matter? It does matter, in fact, and I want to give you a concrete example, and I want to tell you a story, which is a kind of old-fashioned story, because it is about famous or infamous software, which is called TrueCrypt, that was very popular at the beginning of the 2000s, because it was one of the earliest efficient full disk encryption software. It was available for many platforms. Linux, Windows. I think it was even before Lux, that is now the default Linux solution for encrypting disks. It also had pretty much troubled history, somehow connected to the life of cyber and non-cyber criminal that is supposed to be suspected to be the main author of the software. And it has been discontinued in 2014. It has been replaced by Libera.chat, which has a very similar architecture and therefore shares many of the things that I'm going to say for TrueCrypt. So TrueCrypt worked in the following way. So you start from a physical volume, which could be your hard drive, and then you create inside it encrypted TrueCrypt volume. So an area would be allocated for use as a TrueCrypt volume, would be encrypted with a user passphrase or maybe a key file, whatever. And the user would mount would decrypt and mount the partition as a virtual drive that could then be used to access, to store files and protect sensitive information. But the cool feature of TrueCrypt was the plausible deniability. So there was an option to use the empty space into the storage to hide an additional encrypted volume that was encrypted with a different passphrase and would not have a recognizable header, which means that without knowing that passphrase, even forensic analysis would not be able to detect the presence of this external, of this hidden volume. And this was pretty cool and working very nicely in practice, but then something happened. Because people realized that modern solid-state drives, they behave a little bit different from traditional hard drive. In order to not wear too much memory cells, they use systems like layering, trim. So in other words, when a sector of the disk is to be overwritten, it is not really overwritten, but it is just marked as unused. And another fresh block would be used instead. And this would rotate over time. But the consequence of this is that if you analyze the unused space of the disk, you will see snapshots taken at different times of the empty space of the storage. And therefore, a forensic analysis can see that there is differences in this empty storage that would not be present if that space would not be used. And this would allow to detect hidden file system, even without knowing the passphrase. So, and there were cases where this was actually used in court to prove the existence of hidden data. Now, all these problems arise from the fact that access patterns matter. Encryption alone does not hide access patterns. Access patterns are, for example, whether you are performing a read or write operation, what size of data you are accessing, the position of the data. All these things can actually leak sensitive information. And encryption alone is not enough to protect against this leakage. And that's where ORAMs come into play. ORAM stands for Oblivious Random Access Machines. An ORAM is a cryptographic scheme that works as a compiler between a trusted program and an untrusted storage. It works by interfacing the read and write operation of the program and turning them into oblivious access queries to the storage. So queries that do not leak any information, even by observing their behavior from the point of view of the storage. So you can see an ORAM as a compiler that turns a program into another program that is functionally equivalent, but where all the read and write operations are replaced by oblivious operations. From the point of view of the program, however, you can also see it in a different way. You can see an ORAM as a compiler that turns an untrusted storage into a trusted storage. Now, research on ORAM schemes started already in 1987. You can imagine, an easy way to a trivial scheme for an ORAM is the following. Whenever you store all your data in encrypted form, and whenever you need to access one particular sector of data, you just download all the data from the cloud provider, from the external memory, whatever. You decrypt the whole database, you perform your operation, and then you re-encrypt it with a randomized cipher. So this is a cipher that even if you use the same key, encryption of the same data is different every time because you are using a different nonce or a different IV or a different randomness. So, and then you re-upload the whole database. Clearly, this doesn't leak any information because from the point of view of the storage, this is just fresh encrypted data, but it's really inefficient. So this is just a trivial trivial example. Subsequent works tried to improve this kind of schemes in many different ways. All of them share a common blueprint that is basically a trade-off between non-ORAM and ORAM. You store data in encrypted blocks. Each block is identified by an index, a position, and you keep track somehow of the index of the blocks. Whenever you need to access a block at a certain index, you do not download only that block, you download a bunch of blocks. You decrypt them, you perform your operation, you re-encrypt them with randomized cipher, but then you also shuffle their positions somehow, and then you re-upload them. Clearly, this introduces some performance penalty, so you need to reach a trade-off between security and performance. A changing point in the history of ORAM happened in 2011 with the discovery of the tree-based ORAMs, and most importantly, in 2012, with the discovery of path ORAM. That was really a breakthrough moment for the research in the ORAM area. It was very efficient, very easy to analyze and to implement. And even nowadays, that there is still a lot of ongoing research on ORAMs, but many of the state-of-the-art schemes nowadays are basically improvements or evolutions of ORAM. So we started from here, and we built something out of this. And I will leave now the stage to my friend and colleague Niels, who will tell you a little bit more about ORAMs and about what we did with them.
Thank you, Tommaso. So first, I will tell you just a little bit about path ORAM. So imagine we are not using an ORAM at all, and we just want to access a block on a disk. So you would just get the logical block ID and directly access the block using the corresponding physical block ID. But in path ORAM, we don't want to leak that information. So we cannot directly access it by its physical block ID. So it's like we have a read function and a write function. The read function takes a block ID in parameter, and it calls the low-level read function. And the write function takes a block ID and a list of bytes in parameter, and it calls a low-level write function. But in path ORAM, we need some function f that translates the logical block ID into a physical block ID somehow. And the question is, what is that function? So the main idea in path ORAM is we can directly access the block. So what if we access more blocks than what is really required? But then we have more questions, right? Because how do we know which blocks should we access? And how can we be sure that the true block we want to access is within that list of blocks? And path ORAM has a cool solution to that. And it is the following. So we group blocks into nodes, and we represent the nodes in a binary tree. And we keep a mapping between blocks and leaves of the tree. And the reason for that is because there is always a single unique path from the root of the tree to a leaf. And that path contains nodes, and each of those nodes contain blocks. So that defines a list of blocks. So using just a leaf, we define a list of blocks. So here we solved the problem we had. And we can always be sure that the true block we want to access is within that list, as long as we keep a mapping between blocks and leaves. And one other cool thing with that is that we only need to store a very small amount of data on the client side. We just need to store the mapping between blocks and leaves. So here I have a diagram to explain this a little better. So on the right, you see we have a binary tree, and we have nodes, so labeled from 0 to 6. So we have n equals 7 nodes here. And each node has a fixed number of blocks, z. Here, z is equal to 3. And each of those blocks has a fixed size in bytes, for example, 4096 bytes. So the total size of data we can store in that ORAM is n times z times b. And now when we want to use the ORAM and access some data, we first have to initialize it at the very beginning. And initializing it means we have to initialize the position map we see on the left here. And the position map is just a key value table with keys that are the block IDs, and the values are the corresponding leaf IDs of the leaves in the tree. So here in the tree, for example, we have leaves 0, 1, 2, and 3. So now that when we want to initialize that position map, we just have to make sure it is valid for the physical location of the blocks. So for example, if we take block 3, there are two possibilities. So it could be mapped either to leaf 0 or to leaf 1, because there are two different paths from the root to a leaf that contains block 3, right? If we start from the root, we can go from node 3, then to node 1 to get block 3. And then we can either go to node 2 or node 0. So it doesn't matter which one, we just choose one at random, and we make sure all of that matches the physical location of the blocks within the tree. Then we are initialized. So now that we are initialized, when we want to access a block, let's say we want to access block 3, we first look up in the position map what's the leaf associated to that block. And we see that it's associated to leaf 1, for example. We store that value temporarily, and then we generate a new random leaf and update it in the position map so that in future accesses, the path will be randomized. Now we remember what was the value we stored before updating it. So it was leaf 1, and we build the path from the root to that leaf. So we see that the path is node 3, node 1, and node 2. So we get blocks 0, 1, 2, 3, 5, 12, 13, and 14. And we read all of those blocks from disk. We decrypt them because they are encrypted on disk. And we load them in a special location in memory that we call the stash on the left. Now that all the blocks are loaded in the stash, we will go through them one by one and compare the ID of the blocks in the stash to the ID of the block we wanted to access, so block 3. As soon as we find block 3, we do the operation that we wanted to perform. If it's a read, we read the bytes from block 3, and at the end of the function, we will return those bytes. If it's a write, we will update those bytes in block 3. Now we just have to write back the blocks into the tree. But here we also have to be careful because we can only write back the blocks where it's valid according to the position map. So whenever we write back a block, we have to make sure it's on a path where the leaf that's formed from the root to that path is the correct one in the position map. And of course, before writing back, we re-encrypt all of the blocks. So it can happen that sometimes some blocks cannot be written back to the tree directly, so they will stay in the stash and they will be written back in future accesses. But so that's not a problem. So this is what we implemented in a tool that we open sourced that's called ORAMFS. So the code is available on GitHub. It's licensed under GPL v3 and it's completely storage agnostic. So it will work with any remote cloud, Google Drive, S3, remote SSH server, anything that you can mount as a local directory. It's written in Rust, so it should give you great performance and it should avoid any memory safety issues. And we've seen that the size of the ORAM usually is fixed, but we implemented a way to resize it. So when more space is needed, it's possible to enlarge the ORAM. It supports multiple schemes, so pass ORAM and more, and multiple encryption ciphers. By default, we use AES GCM. So not only does it do encryption, but also authentication. So when using ORAMFS, you will need to specify two directories as input, the public directory and the private directory. The public directory is what we can see as the server. So that's the untrusted storage. And it can be anything that appears as a local directory. So you could, for example, use rclone to mount a remote drive, or you could use, let's say, a mounted Fuse file system that creates a directory, anything that looks like a local directory. And the private directory is the client side, and this is what you, the user, will access. And it's just a regular directory where you can read and write files from. So just a few words about the architecture. So we use a local directory as input. Then we use Fuse to take that as input and we expose a single file. That file is called ORAM, and the size of that file is the total size of the ORAM. And from the point of view of a user, it's not very convenient to have just a single file, right? Because you want to have multiple files, you may want to have folders and so on. So what we do is we use that single file as input to create a loop device. Then we create a file system on that loop device and we mount it in the private directory that you specified. And this is the mounted private directory that you will use to write and read files from. So just a few words about performance. So there is a project called UTAFS that is an encrypted storage system made by Cloudflare. It's Fuse-based and supports a few cloud storage providers, but just a handful. And it also supports ORAM optionally, and they also implemented pass ORAM. So we thought it was interesting to compare that one to ORAMFS. We configured UTAFS to use a local disk, and we enabled the ORAM feature. And for ORAMFS, we used the default settings, so also local disk and the default AES GCM. And we observed that roughly 2 times speed up for writes and roughly 9 times speed up for reads. So now I'm going to do a quick demo of ORAMFS. So here I have the ORAMFS executable built already. And first I'm going to create a public directory and a private directory. And then I'm going to add a new ORAM that I will call HR for human resources and pass the public and private directory in parameter. And we will use the default values here. So the size of the ORAM, 16 megabytes, and default directories. Now we can mount the HR ORAM. And on the first mount, we have to choose a passphrase. And since we also do some operations like mounting that require sudo, we have to type the sudo password. And also for changing the owner of the directory. Okay, so now that it's mounted, we can see in the private directory that we have a mounted ext4 file system here. We have the lost plus found directory. So we can create a file inside of that private directory, let's say salary entries, and we add a few salaries there. Okay. And now just to show what happens, if we go to the public directory, inside of that, we have the node files. So this is our untrusted storage. And I'm just going to show which files are updated. So I'm just showing the most recently changed files. And if I, let's say, write a new entry into that file, you will see on the right that every time I write something in the private directory, it has an impact on the public directory. And the node files that are changed are actually different every time. Okay, so also another thing, if we look at our mounted partitions, we see that our ORAM here is 15 megabytes. Let's say, I don't know, we don't have enough space, so we can enlarge it. Yeah, so we first have to unmount it. And now we can enlarge it. So yeah, it's going to double its size. I have to enter the passphrase. That's it. And now we can mount it again. And if we look at our ORAM, it's now double the size. And we still have our files in the ORAM. Okay, so that's it for the demo. So as you saw, ORAMFS will give you increased privacy when you're using an untrusted storage, and it's pretty easy to use, but it's still a prototype. So we have future work that we expect to perform. So there are performance improvements that could be done. We also want to support more platforms, potentially mobile devices, and also implement more ORAM schemes. So for more details, you can get the code from GitHub. There is also a nice blog post that my colleague Tommaso wrote about PathoRAM on our research blog. And if you want more details about PathoRAM itself, there is the paper about PathoRAM. So thanks a lot for listening to us. And do you have any questions?
Yes, thank you.
Thank you.
Thank you. Yes, I have a question.
Oh. Nice.
What is the order of magnitude of the bandwidth increase when you deploy ORAMFS? For example, when you use some cloud storage, you have sometimes price scheme that depends on the bandwidth you're using. So can we get a rough idea?
Yeah, so it's probably, it will depend on the size of the tree, actually. It will depend on the tree height. So the bigger the ORAM, the slower it's going to be. But For example, if we take the tree that we had in that example, it had only 7 nodes in it. So for each of the reads that you do, is there some echo?
No, I don't think so.
Okay. So
yeah, there was some. You can try again.
Okay, sorry. So for each of the reads that you would do, you would have you just want to read one block, but you would still need to read all of the blocks on the path from the root to that leaf that's associated. And then you would need to write them back. So you would at least need to read and write like 9 blocks for that specific example tree. So if you have a bigger tree, it can be even more than that.
So maybe just to add something more in respect to performance. I mean, clearly ORAMs are not really well suited for high performance access, and even existing state-of-the-art solutions are not fast. Now, this is a prototype. We didn't optimize too much for performance. There is, in fact, quite a few extra tricks that can be done and that we are working on. We were actually quite positively surprised by already achieving a very good performance speed up compared to other competing tools, let's say. But yes, there is, of course, there is optimizations to be done.
Thank you. And so the security level depends entirely on the tree size, and of course the overhead that comes with it, or is there some tunable things you can choose for, I don't know, like a very large tree size, but you little bit the security level?
So it will
so
depend.
There is a manual mode.
Yeah.
Oh, go on.
Thanks, Tommaso. So yes, so as Tommaso was trying to say, we have a manual mode where you can actually tune the parameters N, Z, and B that I showed in the diagram. So you can choose exactly how many nodes, how many blocks per node, and what's the block size you want to use. So if you need specific requirements, it's possible to change those parameters exactly as you wish. And the PassORAM paper defines, it has a table with, I think, values for the Z parameter that give a specific security property for that parameter. So you can look that up and see what value specifically you need.
Thank you. There is a question on the Q&A, if you can see it. Otherwise, you can read aloud if you want.
Yeah.
So how does it compare to encrypted stacked file systems such as CryFS or GoCryptFS? So we did not benchmark against encrypted partition solutions because that's not the point, right? I mean, ORAMs offer a different level of privacy, so you shouldn't really compare Apple versus Orange, I would say. But some ongoing work that we are really pops up very often. So we are actually working on a complete benchmarking, comparing different solutions. We hope of publishing it soon.
Okay, maybe just one last question. You were talking in about performance improvements in the future works. What kind of performance improvement you can do?
Yeah, so one thing that could be done is trying to parallelize when we write back some of the blocks or read some of the blocks, because all of those have to be encrypted and decrypted. And it looks like there may be a bottleneck with encryption because there's lots of small encryption operations being done for each of the blocks or for each of the nodes. So right now it's sequential, so maybe we can parallelize that. Another possibility would be to implement other ORAM schemes. So PassORAM is one, but there are others that may bring better performance.
And is it currently implemented as a fuse file system or as in kernel file system?
So it's a fuse file system for now.
Okay.
Yeah, that's a good point. Another possibility is to get rid of fuse and trying to do it in kernel, but that requires a bit of work. It's on the roadmap sooner or later.
I guess that's the transformation from the code.
Other possible improvements that we were thinking is, so first of all, depending on the kind of storage that you have, if it's remote, if it's Google Drive or SFTP, whatever, you might get better performance fine-tuning the N, Z, and B parameters. So something that we are currently researching is having a grid and finding the optimal tuning parameters for a certain set of storage. And there is another possible optimization that we have not done yet because our impression is that it will not really save us a lot in performance, but it will save a lot in local trusted storage requirements, is to use recursive PathORAM. So the idea of PathORAM is that you still have to store in a secure area the position map. But what you can do is to do recursive PathORAM. So every block is another position map. So basically you build ORAM tree made of smaller ORAM trees, which means that you have to do some back and forth communication query to the storage, but your position map on the local storage is very minimal. So if you want to store terabytes of data remotely, you potentially with a few kilobytes position map on the local storage.
Okay, nice perspective.
But it's going to be very slow. So,
yeah, I guess that's the price of privacy, usually. I don't think we have any more questions. So, well, thank you again, Niels and Tommaso.
Thank you.
Thank you very much.
And well, I don't know if we set the timer because it's time already.
No, we are just in time. Perfect.
So last shorter talk will be done by Damien Coquille. He's working at Quarks Lab, which is one of our sponsors. So Damien will talk about a tool to emulate firmwares. So we can see your slides. That's okay.
Okay, can you hear me as well?
Yeah, it's all right. You can go.
Okay, fine. Good afternoon, everybody. I'm going to talk about a little tool I developed, allowing researchers to do very interesting things with firmware, and especially in firmware emulation domain. So just a few words about me, for those who don't know me. I'm a hacker since 1998. I'm also a hardware and software reverse engineer since many years now, and I'm also an IoT security trainer. So I was used to train people on IoT security, and so obviously I know how to hold a soldering iron, I guess. So in this talk, I will cover the origin of this project, why I designed this Piotr tool. Then I will introduce this tool and show you what it's capable of, and some conclusion in order to finish the talk. So, like I said, I'm used to teach IoT security, and in my training sessions, I decided to give the trainees real devices, because the common off the shelf device bought on Amazon. And my first idea when I created this training, and by making or allowing people to test physically on a real device, was to give them a good overview of what can be found in real life on real devices. So it was maybe not the best idea ever, because in one session I stumbled upon a new version of a firmware on a Chinese IP camera I was auditing in this training. And in fact, the vulnerability I was supposed to exploit during this training wasn't present anymore in this new firmware version. So I had to do some research live during this training to find another vulnerability, and we managed to find one and exploit this vulnerability. So this is not what you expect from this type of training when you're a trainer giving this training, you know. So basically, my first idea to allow people to exploit some real life vulnerability on a real device wasn't that wise. So there are also other issues with command off-the-shelf devices, such as if you decide to build or to give a training like this on real devices, you may have to buy a lot of them because they may be discontinued at some time. And it was the case for this Chinese IP camera I was used to use in my trainings. And in fact, I found it on other websites, on other websites, on other sellers' websites, sorry. And it costs a lot. Typically, the price was between 10 to 15 euros. And on this other websites, it was more like 20 or 30 euros. So it's something you have to keep in mind when you jump into this IoT security training stuff. And then the COVID-19 struck, and it was very difficult to send real devices to attend this. There were a lot of delays. Also, the costs were expensive because the French post wasn't that efficient at this time because of the pandemic. And at least, even if a device managed to get to a trainee, this trainee may break it eventually during the training session. Obviously, our training session when we're done remotely at this time. So this, all of these issues made me change my mind regarding the way we gave this type of trainings on devices. So at this time, it became clear to me that I needed a way to emulate IoT devices, and especially for teaching vulnerability research and exploitation, and especially for my Chinese IP camera as well. I needed a tool, easy to install, easy to set up, and easy to use, because I was giving remote training at this time, and it's a mandatory feature. You know, we need to have a very small tool that's easy to use for trainees, because trainees. I needed to be able to send small images of virtual devices, because sending gigabytes of data over the network takes ages to be done. And so basically, a lot of people with a not so good internet connection, for them it was difficult to get the files. So the smaller the better at this point. So the first thing I did was to look around on the internet to see if there is any existing tool that may do the job. So basically, I stumbled upon 3 of them. The first one is a very common tool and very well-known tool, which is a QEMU, which is basically the emulation tool. The second one was Firmadyne. Firmadyne is an automated firmware emulation framework, and it's a product. It doesn't fit the need. I will explain in the next slide why this tool is not the one I was looking for at this time. And I also stumbled upon ARMX, which is a Somil Shah's ARM exploitation emulation platform, which is basically a training-oriented firmware emulation tool. And this one looked pretty good. So just to give you an idea of what is possible with all these tools, so QEMU basically is easy to set up because it comes with a lot of basic and well-known Linux distributions. It's not that easy to use because you need to add a lot of parameters in command line, which are quite obscure for newbies. So in fact, it's not what I was looking for, and also it's also difficult to create a new device since you have to build a whole file system and to compile the kernel, and that's all this kind of stuff. And obviously, there is no export or import feature that was mandatory in order to give a training in good conditions. The second tool was Formadyne. Formadyne is an automated exploitation framework that relies on emulation to assess the security of a specific firmware. So basically, you download the firmware from a vendor website, or you extract it from some flash memory, and then you pass it to Formadyne, and Formadyne does the magic. So it's easy to set up. Not that easy to use again, because you have to give some information to Formadyne in order to get the emulation right. And in for some cases, it won't be able to emulate the firmware because of many issues. The main idea behind Formadyne for its designers was to automate and to automate vulnerability research on many firmwares. So this is not to give training as well. The last one is ARMX, which is a very easy to install tool designed by Somil Shah, and it was used during some IoT security training as well. So it's easy to use. It's provided as a virtual machine. Now it's also provided as a Docker container. I saw this recently, and it's difficult to create a new device as a trainer to add some new devices to this setup, because it was designed to be a ready-to-use emulation platform, and also there is no export or import feature in this tool. So I looked at all these tools. The best shot at this time was the ARMX tool, but in fact there were some drawbacks. First point is that this ARMX tool was already is made of bash scripts, and it's quite limited in terms of functionality. There is also a lot of complex configuration files. If you want to add a new device, you have to modify a lot of files. Like I said, there is no easy import or export feature, and it's not really modular in the way that you cannot easily add a device or remove a device from this system. So if ARMX was able to do the job, I think I would have modified this tool, but I decided to go the other way. I mean, developing a new tool in order to fit the need. Well, this is another tool, I have to say. So I designed Piotr in order to fit my needs regarding the training and vulnerability research. So basically, it's quite like ARMX. It uses a QEMU virtual host to host our target device. So basically, you start a Linux system, a host system, and in this host system, you are going to put the files from the embedded device root file system, and then start a ch-rooted environment in order to emulate the device itself. So basically, it's just running a Linux system inside another Linux system. Piotr relies on Plan 9 resource sharing protocol, also known as 9P2000, rather than Samba. So basically, ARMX is based on uses NFS to provide an access to the host file system, to the target device file system. but it requires some network stuff. You need to configure a lot of things. And by using 9P2000, it's pretty straightforward and really well supported by QEMU. And again, it also uses default QEMU agent to interact with the host. And it's written in Python, and that means it can be easily installed with pip. And obviously, it allows to export and import a virtual device. So this is basically what Piotr does. The software architecture is not exactly the software architecture, but the way Piotr emulates a device is just the following. So basically, you have your QEMU host, your Linux system with the target device file system, and then everything goes in place, and you can emulate the device. You can also debug a remote process running into the emulated device, and Piotr comes with some useful command line tools as well that are able to talk with the embedded agent in the host, and then you can do some interesting stuff. So what if you want to convert a real device into an emulated one? So this is a very well-known methodology, and this is not very different from what you have to do to add a device into ARMX. So basically, you extract the device root file system and you save it into a dedicated folder. You create a set of launch scripts just to be sure that everything starts up the way it's intended to, but without mounting all the partitions. You have to remove all the all the stuff that is not really useful when you run the system into an embedded on an emulated host. So you can decide to stick with Piotr's default Linux kernel, or you can build yours. By instance, by using buildroot, and there is a single configuration file, which is a YAML file that is required to tell Piotr how to find all the pieces, which are basically the kernel you are going to use and the root file system, and some options to give more detail to Piotr on the device, the emulated device your system will be running. And then once you have done all of this, you can run your emulated device with Piotr as well as ARMX. This is exactly the same process, but the tool differs. So if you have a look at this configuration file, you can see that there are some details about the machine, boot arguments as well, and some information about the network, since QEMU is able to redirect and forward TCP ports as well. So this is a nice way to set up a machine to give Piotr a lot of information about how the machine must be created, the emulated system, I mean. And that's it. Once you have done this with the root file system and the kernel to use, that's okay. Exporting a device is quite easy once a device is created and tested with Piotr. Then you only have to use the export command to create a Piotr file that may be shared with other people, and other people can also import this device as well with a single command line. And everything is handled by Piotr, all the kernels, root file system, and so on. So this is pretty easy for trainees, for instance, to install a specific device into their systems. So with this feature, it's very comfortable. It's very easy to share virtual devices. And if a trainee doesn't manage to make something work on an emulated device, then he can share this device back to you, the trainer, and then you can even launch this device, see how it works. So it's useful when you give remote training and remote training sessions, obviously, to guess what's happening on the trainee side, and which is not really easy to do actually. And then just to end with this presentation of Piotr, not the presentation itself, there are some features that may allow you to debug a remote process in the emulated system. So it embeds a GDB server as well, and since it's written in Python, you can instrument this other devices with Python. You can access a running emulated device. With Python, you can attach a debugger to a remote process and then drive this process remotely with Python again, since it's compatible with Avatar 2 GDB target, which is a very nice feature of Avatar 2, allowing you to drive remotely a GDB server instance. So this is basically how the Piotr works and what are its features. So I'm going to do some demos just to show you how easy it is to get all of this. And my first demonstration will be an exploitation of a vulnerability in an IP Chinese IP camera, sorry, which is basically you need to feed the camera with an SD card, which will be emulated as well. And if this specific shell file is present in the SD card, then it will be launched, and boom, that's it. So I'm going to show you how this can be tested inside this emulated environment. So basically, I have just to give you more information about it. So I have some devices in my Piotr folder, and there is this IP camera, which is a Chinese IP camera, and in this IP camera, I got a SD card, and in SD card, I have this shell script, and this shell script simply starts a tented server. So basically, I'm going to launch this device using Piotr. So by typing this type of command, this Piotr device start IPCam. We need a root password or root access just to get the network working and the file system working as well. It starts the host system, and in the host system, I launch the target start command just to start my IP camera. And as you can see, there is some information about a service that has been launched thanks to my shell script on my SD card. And if I connect on my localhost on port 22223, which is forwarded to port 23 on the emulated system, then I get a shell. So this is basically it. And as you can see, it's easy to modify the scripts, so modify the exploit without having to copy the files on the SD card. And it's it's quite straightforward to do. And I can stop the emulated system this way. So basically, this is my first demo. So yeah, demo gods was with me. I'm going to show you that it's possible to emulate also a random device such as the Teltonika Rutex 10 wireless router. And this is basically the same. I'm going to start the device with Piotr, so like this. This is the Rutex 10. And normally it will start. So basically the host system is launched again, but this time it will use another device directory. And if I go to this URL, I will have the administration page. And if I log into this administration page, I get access to the system. So this is a web server running on this emulated system. You can see that there are some error message on my left. And that's it. So you get some funny stuff since all the devices are not mounted and not working on this emulated system. But this is very useful if you want to search for some types of vulnerability. And with some efforts, it's possible to emulate the whole system and some devices, but it takes some time to do so. So that's it for the second demo. And the last one is an example demo of an automated exploitation of the damn vulnerable ARM router, which is basically a vulnerable device, embedded device created by Sumit Shah for his training that is available on the internet. And there is a Lightsurf service that is vulnerable to a buffer overflow. And then with a small script, I'm going to start an emulated device and as well exploit this vulnerability. So basically, this script asks for a DVR emulated system, create a background instance. So there is a QEMU running in background that will be started. We wait 10 seconds for the system to boot up. Then we launch the target system, which is the DEM variable ARM router. We wait 5 seconds, and then we get the PID of the light serve process. And once the PID is recovered, we attach a debugger to this process. We configure GDB to follow to follow the child processes as well, and we trigger this buffer overflow by sending a payload to this port on my local machine, because it will be run on my system, and we are waiting for the process to crash. When the process is crashed, we get the program counter, and obviously, since we are sending a lot of A's, it will be 41, 41, 41, 40 on this ARM architecture. So I'm going to use this Python script to launch this automated exploitation. So here we are waiting for 10 seconds for this device to boot up. So the host system is running in background. Then we start the emulated guest, which is the embedded device. We wait for the PID to be found. That's it. We trigger the buffer overflow, and we read the program counter register from this debugger. And as you can see, it's the expected value, which is full of A's. And that's it. It's quite easy to automate all of this. And of course, for training, this could be interesting to give trainees some kind of automated exploitation, just to show them how it's done, or to give them a template to perform this kind of exploitation. You can also imagine what can be done with this from a researcher perspective when you are looking for vulnerabilities, automating exploitation, and so on. So this is basically what Piotr is about. As a conclusion, Piotr provides a Docker-free, network-free, QEMU-based device emulation environment. It emphasizes on ease of use, sharing, and automation. It can be used to build other tools, obviously. And it's compatible with ARMX. This is not a replacement for ARMX, but a complementary tool in order to emulate devices. So if in the future more devices are included with ARMX, they are also compatible with Piotr and so on. So, and also devices created on Piotr may be compatible with ARMX as well. If you want to give it a try, you can use it and install it with pip. There is also documentation available on the internet with the docs. And if you want to have a look at the source code, you can clone my Piotr repository on GitHub. And that's pretty much it. So if you have any questions, don't hesitate.
Thank you, Damien.
Thank you very much.
You on the chat, you have a thank you message from Somil Shah. That's nice.
Hi, Somil.
So there is one question on the QA.
Mm-hmm.
Someone asking, does it support bare metal?
It doesn't support bare metal at this time, because most of the devices we use during trainings are Linux based. So it's I don't know what the extent of the bare metal term used by the person who asked the question, because it can be very low level. But in fact, it's at the moment, it only supports Linux embedded systems and on ARM platform. So it's if you find some MIPS architecture or the different architecture, then it won't work with Piotr.
Yeah, that's well, that's similar to the question I had in mind. Kind of a noob question, but I was wondering. So QEMU is your founding stone. I mean, and I was wondering if there are many. Well, if you can, of course, you can find devices that won't be emulated by QEMU.
Oh yes, sure. There are some devices you won't be able to emulate with QEMU because basically the QEMU provides a very generic platform called Virt, which is compatible with some ARM CPUs, but it's quite limited at this time. There are only, I guess, maybe 2 CPUs that are supported by this platform, and it's the best platform we can use to emulate stuff. There are also other platforms, but at this moment, I also only implemented this Virt platform into Piotr. So if you have some specific hardware on so for instance, this won't work because QEMU is not able to emulate this kind of peripherals. So that's it. It's very limited at this time because QEMU is limited. It's difficult to emulate specific hardware on this system. So the best way we can achieve emulation of this type of embedded device so far is just by removing all the annoying stuff, by mocking some devices or developing some specific drivers that behave like the original ones, but without requiring some specific hardware to be connected to the device or to the emulated device, to be more precise. But this is obviously there are limitations to the system, but the point is, if you're giving a training, you're supposed to find a device that suits this situation. I mean, you need to find a device without a lot of hardware requirements. If a device uses a lot of specific peripherals which are very specific, then you won't be able to emulate this system, and most of the services used on the device won't work.
Yeah, of course, yeah.
I don't know if it answers the question, but maybe I got it wrong. But this is basically.
I guess it can also contribute to enrich QEMU and the devices that it can emulate.
Yes, but I think there are a lot of different devices, different peripherals on this huge amount of devices you can find on the internet. And in fact, you have to develop some specific mockups for each peripheral you want to emulate. So it can be done. It takes just time to achieve this simulation. So it's a huge effort to make all the devices emulated on QEMU. But in fact, I'm quite sure that someone can achieve this, or maybe a lot of people can achieve this. But in fact, it's a community effort. We need a lot of people to implement all of this and make it compatible with QEMU, just to be able to say to QEMU, well, there is this type of peripheral connected on this specific bus, and so on. It's a huge work to get it working. And in fact, since a lot of components and peripherals evolve very quickly, we have to reverse engineer all the drivers to guess how it works and what are the expected value sent by the services or the firmwares or processes that use these peripherals to get them working well. So it takes a lot of time. So basically, this is why we most of the trainers using this kind of emulation decided to just remove these parts and keep only the running services running by using some tricks rather than emulating all possible peripherals, I guess.
Okay, so there is more on QA. Someone is asking to show the GitHub link, so maybe you can just put back the slide. So that's done. Then, well, I don't know if you can see the QA window, but that's not.
I don't know.
Maybe that's not easy with the screen sharing. So
exactly.
So Mil asked two questions.
Yep.
First question is question with Plan 9, so the 9P file system.
Yep.
He said, I struggle to have it implemented in all kernels like 2.6. Can you confirm if this struggle is real?
Yes, it was added into kernel 3.5, if I remember well, but yes, he's right. If you are using an very old version of kernel, Linux kernel, this is not compatible. So this is also why Piotr, I didn't mention in the slide because I only got 20 minutes to go through this topic. But in fact, in the configuration file, there is an option to integrate or to embed the target file system into the global file system of the host in order to avoid all of this. So it's less convenient since once the emulated device is started, then you won't be able to access the file on your file system from your Linux system that is running QEMU. But in fact, it solves the problem of this Plan 9 with the resource sharing protocol. But most of the devices I've stumbled upon these days, or most of them start with the Linux kernel version 3 to Linux kernel version 4. So I mean, it won't be a problem in the next few years anyway, when not so old version of Linux will be used. But I also found some devices that, like Somil, I guess, were based on a Linux kernel version 2.6 or similar. And then, yeah, this protocol is not supported, and this is why I did this embed option. You have to give in the config YAML file just to tell Piotr to embed the files rather than using this protocol to share the target root file system. But,
okay,
yeah,
nice.
That's the point.
And maybe last question also from Somil. Have you had any luck with Broadcom's NVRAM kernel drivers?
Sorry, can you repeat the question? I think I missed something.
The
Nope, I did not have a look at this NVRAM stuff from Broadcom, but in fact, just to mention it, I didn't include the NVRAM stuff Somil developed and used in his ARMX platform because it's a common way to solve this NVRAM issue. So NVRAM is non-volatile random access memory, which stores basically some parameters of some devices. It's well explained in Somil's documentation on ARMX, but I plan to add some support of it in the next maybe the next month or maybe the next releases to make Piotr more complete. But in fact, I didn't dig into this Broadcom NVRAM stuff. No, I'm afraid.
Okay, well, he says it's a hacky job.
But it could be interesting to maybe to collaborate to solve this. Yeah, this could benefit both ARMX and Piotr, I guess.
Okay, and maybe one last question. Someone asked if the MIPS support is in the roadmap.
MIPS support is in the roadmap, but the main issue is that QEMU doesn't support well this MIPS platform. If you have a look at what with a lot of different types of emulating machines, while the MIPS platform maybe got maybe three or two, I do not remember well, but this is very limited support on an emulating machine. I mean, some communication buses allowing this CPU to communicate with peripherals and so on. And this seems limited on the MIPS platform. So I don't have a good idea of what's possible to run MIPS-based software on this on QEMU. But I think it would be interesting to try it. But at the moment, I'm not sure to achieve this with of QEMU.
Well, okay, that was a nice QA session, I guess. So, and the talk here. Thank you, Damien, again.
You're welcome, and thank you for selecting me, I guess.
Thank you.